everyone, welcome to this interesting session on deep learning with TensorFlow full course. So before we start with this session, let's take a look at topics for today's session. So we'll start today's session by understanding what is artificial intelligence, what is machine learning, and the different types of machine learning. Once you understand the different types of machine learning, we'll look into the limitations of machine learning and how deep learning solves it, and then we'll look into the real life use cases of deep learning. Once you go through the use cases of deep learning, we'll look into how deep learning works, how neural network works, the neural network components, and then finally get into what is TensorFlow. Once you understand what is TensorFlow, we'll also look into how TensorFlow works, the TensorFlow functionalities, and then look into what is perceptron. So once you understand what is perceptron, also we'll finally end the session with perceptron examples. So today we have a special guest, Amit, who's going to take this session forward. So over to you, Amit.
Hello everyone. Welcome to the course, which is Deep Learning using TensorFlow. And my name is Amit. I would like to give a small introduction about myself. My name is Amit. I have got around 12 years of experience in the field of machine learning, data analytics, and deep learning. And for the last 4-5 years extensively, I have been working in the field of deep learning as an independent consultant. I'm a mathematics graduate and have done my master's in applied mathematics and have done numerous certifications in the field of deep learning. I have worked on deep learning projects involving NLP, computer vision, and other structured data analysis for different industries and companies as an independent consultant. If you have not installed TensorFlow and Python, please go ahead and install on your systems. So that's the first requirement. So let's get started. So first thing which comes to our mind, there have been a lot of emphasis on this term called artificial intelligence. So let's first try to understand that what is artificial intelligence on a very high level and why we may need it in first place for solving a problem. So let's try to understand with an example. A person goes to a doctor and he wants to get checked at whether he got diabetes or not. And what doctor would say is, okay, there's some tests which you need to get done, and based on the test results, doctor would have a look, and from his experience, from his studies and previous examples, the patients he had seen, he would be able to evaluate the reports and say that the patient has diabetes or not. So if you just take a step back and think, I said that doctor has experience. So what do we mean by experience? The doctor has learned what are the characteristics of somebody having diabetes. Will it be possible if we can provide this experience in the form of data to a machine and let machine take this decision whether a person has diabetes or not? So the experience which doctor learned through his studies and his practice, what we are doing is we are taking customers' data who have with different reports and different parameters on different things like the glucose count in blood or the weight and height and all these parameters about a human being. And based on that, we have fed it to a machine and tell that what are the characteristics of a person who has diabetes. And from this, let's say we have 1 million customers data we have given to a machine, and let machine do this stuff from his experience, from a machine's experience, which comes from the data or historical data to be precise, and do the same task which a doctor is doing. So what we have done is, if you see from this example what an artificial machine or artificial intelligent machine is doing, that it's learning from the historical data and trying to do the same thing which an experienced and intelligent doctor was doing. So this kind of area or domain, we can activities which human beings were doing, if we can make machine intelligent enough to do the same task. Why we should create these artificial intelligence based machine systems, there are some on a very high level, there may be a lot of points, but if we just discuss a few points, that human beings have limited computational power, and we guys may be good in terms of classifying things, like you can see your friend in a group photograph and easily can say who is your friend and who are others. You can easily listen to a language and comprehend what a person is doing. But human beings are not very good in doing a lot of mathematical. If you try doing good amount of mathematical computations in your head, probably it will not be very easy. And second is that it's not possible for human beings to work continuously, let's say 24/7 a day for 30 days continuously. If we can make machine do such stuff, one, they would be able to kind of do these computations very fast. And like I know we spent a good amount of time in discussing the GPUs. And I also mentioned that Google is talking about a TPU machine, transfer processing units, which would be hugely changing the entire paradigm of computations, and machine would become more and more competitive or even better than human beings in some of the fields. This is the formal definition, but if I loosely translate, it's basically that artificial intelligence machines are those machines which can do tasks which human beings can easily do. So things like identifying what's written, let's say in a license plate, or playing games, and I'm sure some of you would already heard that machine have defeated the Go champion and the chess players already. Now we have digital agents like Siri and others which can understand what we want them to do and can take intelligent decisions from the text or from the voice itself. Though the application is huge, and basically these are very high level, and some of the fields where deep learning has made a great inroads, something like game playing, expert systems, self-driving cars, robotics, natural language processing. And I'm fond of natural language processing. I am currently working on a chatbot on one of my projects. So this is one area of interest for me. So there may be different and new areas where we are implementing. All of you know that every experience of human beings is getting digitalized. The kind of things you buy, kind of things you watch, and what your preferences are, who do you like on Facebook, who you don't like, what kind of movies you like, and all these things in terms of reviews being captured online. So once your data is going and captured online, there are systems which can analyze this data. So given this huge data generation, as well as now we have machines which can process it and make some intelligent decisions are available. So that's why you will see there have been a lot of emphasis now in last couple of years. A lot of new things are coming in. Some of you who have been reading these papers on different subjects, different architectures would know that most of these architectures are not very old. It's a very dynamic field every day. In fact, on a weekly basis, you will be hearing about a new API or a new kind of architecture being developed by somebody. Most of the stuff we will be studying in these classes are not very old, like convolution neural network and recurrent neural network. Some of their variants are as new as last year. If you guys follow TensorFlow closely, they introduced a library called Object Identification. Object detection API, which TensorFlow has made available for everybody. You would be able to see it yourself that this API works. There are 5 different options of selecting different deep learning architectures or convolution neural networks for this API, but it's been able to identify human beings and all other 90 objects there with almost 99% accuracy. In some cases, from even human beings would be finding it difficult to kind of see and predict what the object is. But this machine has gone even beyond a human capability in terms of identifying objects. Given that we have a fair understanding or very high level understanding, we haven't gotten into details of artificial intelligence, but basically from a loose understanding that artificial intelligence of making decisions or machine making decisions which human beings were earlier doing the task, something like game playing and natural language and drivings of car. Let's understand how this machine learning and deep learning are related to artificial intelligence. So basically artificial intelligence is a bigger domain. So if you look at robotics, there involvement of a lot of things. There is mechanical inputs, that how a machine moves, it's some dynamic kind of agents and all other things. Within artificial intelligence domain, we have machine learning for solving business problems. So you can think of it on a very high level that machine learning is kind of brain for artificial agents. So all the data we make it process, make machine learn, whether it's one class or other class, these kind of decisions are being taken or being learned through machine learning algorithms. Within machine learning, deep learning is further subset of machine learning. So people who come from machine learning background, all the algorithms like regression, logistic regression, decision tree, random forest, or support vector machines, these were the algorithms you would have been working till now, and I'm sure these are very powerful algorithms. Some of them are really helpful in solving a lot of business problems. But the deep learning is a different kind of architectures which do similar tasks. So when I say similar tasks, I mean that either predicting some numerical number, let's say what would be the sale next month for a company, or if I need to do classification tasks, whether somebody will pass an exam or not, or if we need to identify some objects within the image, if I need to translate language from one type of language to another one. So all those kind of activities or problems which machine learning algorithms were not able to solve till now, these algorithms are being able to solve. When we go through the deep learning architectures, we would kind of being able to see that these machine learning algorithms like regression or logistic regression still are very much relevant in deep learning, and a lot of learning or a lot of building blocks of deep learning take intuition from these algorithms. And this is one of the reasons that we have included some of the basic algorithms like regression and logistic regression in class, so that we can explain you some bit of it, that how do we identify and some steps in terms of how do you prepare the data to make your model learn, and what kind of steps you need to take to prepare your data, which would be common also not only in machine learning algorithms, but they will also be common in deep learning architectures as well. So if you look at this, let's say we have data on some flowers, and flowers, different aspects of it like sepal length, sepal width, petal length, and petal width. These are the features, and features can be information about a product or a customer or anything. Let's say we are talking about a customer, then the information can be that what stage of the customer, how much does he earn, or how much does he spend every month on the company products and all. So these are some information points. And once we give this data, your machine would be able to learn from the data itself whether it belongs to a species of flower A or a B or C or whichever different kind. Basically what it is that earlier systems, any system, were used for solving such problems. People used to hand code these rules that, okay, if this feature is that much, then this is class A, and if this feature is less than that, it's class B, and all that of these things. These were hand coded rules. However, when we do machine learning, as I was saying, it learned from the data. And once it has learned from the data, we can give a new input. And when I say new input, I mean that the information regarding different features of the flowers, the same sepal length, width, and all. And because your machine has already learned, it would be able to classify that which class this particular flower belongs. Given this learning, that now your machine is able to understand and learn from the data, we can solve multiple business problems with the help of this. So let's take a very small example, the same example which we took earlier when we started discussing about artificial intelligence. It was like whether a person has diabetes or not, and I was mentioning that this kind of decision being taken by the doctor based on the reports he has got. And these reports have some numbers, like number of time a patient had a particular kind of issues, or what is the glucose count, and what is BMI, and what the person's age. And based on these numbers, the doctor was able to make this kind of decision. We can take the same analogy where we were trying to predict the flower, which species of flower it is. We can take information of patients and different attributes on different features of a report and the patient, and the machine would be able to learn from these data sets, and for a new customer or a new patient, it would be able to classify whether the patient has diabetes or not. So there are two sections of it. First one is the information about the patient and different characteristics of his health. So from this, which is number of time and glucose count till age, these are the information points about the patient. And the last column is the information whether the patient has diabetes or not. This kind of problem where we have some information points where they explain what the situation is, and other in the last column, or the information of output is in some kind of classes. There is a specific type of machine learning problem it is. But as of now, the characteristic is that we have some information about the patient, and the last column is telling me whether the patient has diabetes or not. So what your machine basically learns that it learns all those rules in the example which I was quoting, that earlier cases people used to create these hand-coded rules to predict whether an event will happen or not. But in machine learning, your algorithm will learn from the historical data and see what are the combinations which decide whether a patient has diabetes or not. And these combinations would be of something of this type. It is only for illustration, nothing to be, it's not the real numbers, but it's for illustration that your machine or your machine learning algorithm is being able to identify these rules based on the historical data. So after learning, it has created the glucose count is less than 99.5. If yes, then go to next one. If no, the person does not have diabetes. If glucose count is greater than 166.5, yes, the person has diabetes. And if no, then there are further drill down of rules. So all these combinations or rules are dynamic in nature. And what I mean is that these rules would be changing if your data set changes. And you can take the same model, can do the work whether a patient has diabetes or not, and you can take the same model and make it learn on a new data set, let's say flower species, it would be able to learn the new rule from itself. So the intuition, like human beings were learning from examples, your machine learning algorithms also learn from examples. But just to frame our problem statement, that machine learning, we know it learned by experiences and from the data from the historical events. There are three kind of problems which may be interested in solving. First one is called a supervised learning problem, and supervised learning problem is basically occurs when you have some input variables and one output column. So both the examples which we discussed till now, one was on the flower species where we are taking data on different features of a flower and then which species of flower it was. So the last column is the dependent variable or output variable we are trying to predict. And all the information variables are called input features or input variables. So input features or input variables, it's kind of interchangeably being used in different texts. Input and output, these are the two different sections of supervised learning. Why it is called supervised learning? Another take, if I need to explain it, that we have a column to guide the algorithm whether it's making the correct decisions or not. So let's say your model says person has diabetes, but the actual data says the person does not have diabetes. So you have some kind of correction mechanism within your data itself, which can help your model tune itself to make better predictions. So this kind of output variable, some text it's also been called a teacher variable. So it's guiding the algorithm to decide those rules which I just go through. Another type of machine learning is called unsupervised learning. And in unsupervised learning, we have only the input features. And our objective is that we should be able to identify the patterns within the data itself. So some of you who are working in telecom domain or marketing campaigns, you would be very much familiar with segmentation analysis or cluster analysis, where our objective is to identify coherent groups within the larger population. We take the customers as it is the whole population, and based on different parameters and variables, we identify some of the groups of customers or products, whichever the business problem is, to identify which are similar in nature so that we can take either marketing campaign or develop new products for those specific groups. Final is called a reinforcement learning. A reinforcement learning is a kind of learning where the agent learn from the environment. So it works kind of reward and penalty. You can think of a self-flying helicopter. So you leave it in the environment and it will be deciding based on the wind speed and other parameters in the environment that how much it should fly. And the reward is that the fuel should be efficiently be spent and more time it should be spending in the environment. So supervised learning, as I said, that the objective here is that we have some input features, and input features would be holding information about different aspects of a given problem or customers. And we have an output variable which would be explaining whether the event happened or not, some kind of output variable. So there are two types within supervised learning. One is called as regression, second is classification. And the differentiation happens only because of the type of output column. If your output column is the type of numerical values or continuous values like numbers, so that would be a regression kind of problem, a very high intuition level. For example, you're working on a problem where you need to predict how much would be the sale of your company given the information that how much they're spending on marketing, how many employees are working, which month it is of the year. And if you have this information, you are going to predict what is the $1 million of sales your company would be doing. So these kind of problems where your output variable is of numerical values, then it's a regression problem. On the other hand, if the dependent variable is of categorical nature or of discrete values, it signifies that it's a classification problem. given that it's a categorical values, your objective is that how you can put the different customers or products into different classes. So that's why the name suggests classification problem. So as I said, there are two kind of supervised learning problems. One is regression, another one is classification. So let's take a use case where we need to predict the housing price of a particular locality. And we have information about these houses on different parameters. And these parameters are like these. So let's say, what is the crime rate in that area? How old is the home? The distance is how far it is from the city. This is from Boston housing data. So this is, if I'm not wrong, it's percentage of black population or some variable. We have the description later on, and what is the actual price of the home? And all these features from crime to ISTAT is the information about the house. So these are my input features. And the output feature is the price of the house. This is in $1 million. And our objective is that we should be able to fit an algorithm that it should be able to learn from all the historical homes which were sold based on all the features and what was the price it was sold for. And once the model is trained, it should be able to predict that how much should be the price for a given home. Let's take an example. Let's say one of you is interested in buying a home in the Boston area, and you would like to know that what is the ballpark figure for a 2-bedroom flat, which is of some square feet and let's say 20 miles from a specific location. What should be the price? So one way would be you go and talk to people and try to understand that what has been the average price. Or if you have this kind of algorithm available which can help you understand that given these features, that was the price, and if you can create a regression model, it would be able to help you that given some features of the new home which you are interested in buying, what should be the price of it? So as I said, there are two sections. One is the independent variables, all these information about the home. And the last variable is dependent variable, which would be information about what was the price. You see this is a kind of scatter plot between the distance from the city and price for the home, keeping all other variables constant. We are not looking at the influence of other features, but we are looking if we just need to model or if we need to find a relationship between the distance from the city and what is the price. From this graph, you can make out that further the city house is, the lower the price would be if we keep all other things constant. So here it's like if we can identify this kind of relationship, though it's called linear regression, maybe the line is not very linear, but for a given distance from the city, you would be able to predict what should be the ballpark figure for a house if you just have this information, not all other information which we have talked about. In a similar fashion, how it's been done is that there would be a relationship between the price of the house and all the features which we discussed. So this is only a relationship between one of the variables, distance to the city, and the price of the home. In a similar fashion, we would be able to find relationship between the price and all other features. So all other features, if you know, like how old is the home, how big it is, what is the crime rate and all. So this kind of model is called a regression model, and it's a very basic equation of a straight line. Y here is called the dependent variable, A is intercept, and B is called slope, and X is called independent variable. If we go deeper and try to understand what it's basically doing is, this equation is trying to tell me that if I already know the relationship, if I know the value of A and B from my historical data, which is about different homes, given the value of X, I should be able to calculate the Y. Y in our particular example is price of the home. Let me try give an example what slope means. So slope is what is the change in dependent variable if we change X, which is the independent variable, by 1 unit. So let's say if I change X by 1 unit, how much change in happen in Y? Help me understand what is the kind of relationship between X and Y. And A is the value which tells the value of Y when the X is 0. And you can think of it something like in the text it used to be like that if you put the value of X equal to 0, whatever the value is Y, then that's the intercept. But basically from intuition perspective, you can think that an intercept is the value which is there even though you don't have any information about X. For example, we were discussing the relationship between the distance from the city and the housing price. Even though the house is exactly in the city, then there would be some value, and even though the house is 100 miles from the city, there would still be some price. So it helps us kind of intuitionally understand the relationship. It also helps the line to understand where it start, whether it start from the origin or some place within your axis. And this kind of equation is called equation of linear regression, because if you see here the power of x is 1, so that's why it's linear in nature. And it is also that we are fitting the relationship between x and only one of the variables. Multiple regression, where what we do is that instead of finding the relationship between only one variable and the dependent variable, in most of the practical scenarios, the dependent variable y is dependent on more than one features. So for an example, your house price is dependent on all these features, all these information points available, and all you want is that your regression model would be able to identify a relationship giving all the information together and then predict what is the price. The equation becomes y equal to b1x1, b2x2, or b3x3, this kind of equation, where b1, b2, b3, and all these coefficients help us understand that what is the contribution of a single or of a given variable into your regression equation. So let's have a look at how you can fit this model in Python. So if you look at the first block of the code where we are saying import panda as pd, import numpy as np, and import matplotlib as plt, this is the convention in Python to import some of the libraries which we would be using. So these are the libraries which are required for running this module or this regression model. So once we import these, all the functions available in these libraries, we can call them very easily. And we will be seeing that how you can call them. So once you have imported these libraries, if you see that we are loading the data called Boston, and that this is the same data set which we have been discussing in terms of a use case here. So next line of code, so here we are importing the data and loading the Boston data set. The next line of code, we are calling the pandas library because we have imported the pandas library as PD. Then we are calling a function called data frame so that we can create a data frame in Python, and we were creating it boston.data. So it will be creating boss as a data frame. So data frame, on a very loose term, you can think of kind of spreadsheet kind of format where your data is being put in rows and columns, and you can think of an Excel file kind of framework for a data frame, though it will be different, but just for intuition purpose. And after importing, I am calling .head. So what .head does, it will be giving top 10 rows of my data set. So there are all the 13 columns. In Python, index start from 0. You can see that index started from 0, 1, 2, 3. So you can see what this data is. This line of command which says .columns. So .column gives you all the features available in your data set. So these are the different feature names. So these are the different column names for the data, and the price. In the end of the code, I have written actually one line of code which can give you all the details, that what the target variable is, what was the history of data, where it was recorded and all. So you can easily look at this. We are calling this boston.target and we are calling it as a boss.price. So we are creating a column in our data frame which was boss from boston.target. So there is another data vector available in the Boston data set itself. And now specifically we are saying y is equal to this particular variable. Y we will be representing our dependent variable. All the features plus the Boston price. So boss.drop price x is equal to 1. It means that we have dropped the price variable from the overall data frame, and x is 1 specify that we are removing the column. So x is 0 represent the row level operations in Python, and x is 1 represent the column level operations. Print statement, we are just printing now the x. So this x is all the input features of our data set. So all these columns which we will be using for predicting the housing price, and how it will be working. So it's not an actual model. But what actually happening is, once we have created the model, it will be doing that, it will be fitting a line which would be going through the actual data set, would be something like this, that price is equal to some intercept term plus b1 multiplied by crime, b2 multiplied by another variable zn, then B3 multiplied by another variable, and so on and so forth. And this intercept and B1, B2, and Bn would be the coefficient which your model would be learning from your already available data. And here we are showcasing the top 5 values of our housing price. So Y is the dependent variable, and we are looking at what is the top 5 values. So this was only a very brief and very basic introduction that how do you import our data, how you can see what are the different columns. It has nothing to do with machine learning, but it is only for people who are new to Python and for people who have been out of touch in Python if you just want to brush up skills. And this line of code, if you have a look, which I'm highlighting now, we are using a scikit-learn model for test, train, split. And what it's doing is for both, because we have already X and Y, the test sizes we are saying 0.33. So it's basically we are randomly selecting 33% of the data we are putting it separate in the test bucket so that we can test it later on. And this random state 5 means because we'll be randomly selecting. If you specify a random state, every time you run this code, you will be selecting the same set of elements from your data set. And it helps you understand that the variation, if you run the code multiple times by changing, the variation is not coming because of the selection of sample. It should be because of the different model changes you are making. This dot shape function in Python specify that what is the dimensions. And if I mention the first one, xtrain.shape is giving me 339 and 13. Basically, it's telling me that there are 339 rows and 13 columns in the data set. Xtest, there are 167 rows and 13 columns. And your Y-test is just 339 rows and there's just one column, or it's just one vector. The number of rows in Xtrain and Ytrain are same. And Xtest and Ytest, the number of rows are same because they have been selected for the same combination. So same houses, we have selected the input features as well as the corresponding values of output, and same has been done for the test section. What we are doing here, as I was saying, that we have imported a library called scikit-learn. And scikit-learn has different modules for different machine learning algorithms, and linear regression is one of the modules in scikit-learn. So we can call this scikit-learn module from linear regression called LM, and this equal to in Python is called assignment variable. So we are assigning LM as a linear regression module in the scikit-learn. And now what we are doing is, if you look at this line only, lm.fit, so basically we are telling that use the linear regression module from scikit-learn and fit the model between Xtrain and Ytrain. So basically what we are telling the model that you learn those coefficients for different X values given Y values in the training data set. Basically what the fit function does, it calculates the values of your intercept, B1, B2, B3 for all the features in your input features for a given Y variable. So once we have fit in the model, and once that has been fit, we can use the same model for doing the predictions. So let me remove it. It should be like this. So lm.fit, we have fit in the model. And once that has been fit, we can use the learned model, which is lm, with a function called predict xtrain. So what it will be doing is, once it has learned those coefficients, B intercept and B1, B2, B3, for all the features in input, you can use the predict function for making the predictions for your training data set. And you already have actual values as Ytrain, and then you can compare that how good your model is doing. And how you can compare it, that if you look that we are put together same thing we have used for the Xtest data set, lm.predict Xtest, and again the prediction has been done. So if you see here, I have put together as a data frame Ytest and Ytest bread, and the difference look like this. For the first value, which was 37.6, and the actual value was 37 point this value. Then the predicted value this, actual value is this. And this difference between the actual value and the predicted value signifies that how much is the error in your data set. So had it been that your model is giving the same prediction as it was the actual value, you would say there is no error, your model is 100% accurate and all the predictions being made by the model is absolutely bang on. But normally it doesn't happen. You end up having predictions which are a bit off from the actual value, and we measure the difference as one of the characteristics or one of the parameters to identify how correct your model is. In this particular statistic, there are two metrics being used for identifying, but the most basic one used is called mean squared errors. And what mean squared error is, it is basically the difference between actual value and the predicted value by the model. And what I mean by this is that let's say this is your predicted value 37.6 and this is your actual value. What you do is you take the difference of these two and then take the square of it. Why we take the square of it? Because this, in some values the difference may be negative or positive, and if you sum it up the difference may come to zero, and you may end up thinking that okay, a model is doing really good stuff. To avoid it, what we do is that we take the square of it so that the difference between actual and the predicted becomes positive, and you can sum it up to showcase that how far your predicted values are from the actual value. And then you take a mean of it to showcase that what is the mean difference between the actual value and the predicted value. It can also be used for model comparisons. Here I can show you that how it is working. That let's say you have some actual values, something like this, and let's say you fit a model, I fit a model. So there is one model prediction 1, another model is prediction 2. So what you can do is you can take the difference between the actual and the predict. So 10 minus 2 is 2, and then you take the square of it, which is 4. 23 and 21, again 2, square of 2, 4. Then third one, the difference is 5, and then square of it is 25, and so forth for all the values. You get the total value of sum of squared errors, and you divide it by the number of inputs, which is 5, and you get the mean of the squared errors. And you do the same thing for the second one, and if you see it is very less, 5, so probably it would be able to help you understand that which model is doing a better job in terms of predicting the housing prices or any other numerical variable. And there is another statistic which has been used for identifying how good your model is, which is called mean absolute percentage error. And that's basically the absolute difference between the actual value and the predicted value, absolute terms. And you sum it up all the values for all the entries and divide it by number of all the value of absolute value of your actual values. And it can help you understand that what is the average percentage your values, the predicted values, are different from the actual values. So sometime if you see, it will be somewhere in percentages. So what I've done is I've taken the absolute difference between this value and the predictions. I sum it up and divide it by the sum of my input values. So whatever value comes in, you can say, okay, it's 5%. So it will be fair to say that your model is 5% off from the actual values, or the error term in your model is, let's say, 5% or 6%. And whatever predictions you're making from the model, you can keep a buffer of that percentage when you share it with the team. And what I mean is that let's say your mean absolute percentage error is around 10%, and it's about the sales of a company. So when you share this forecast, you say that my predictions are around 90% accurate. There may be actual sales, maybe plus minus 10%. So this can help you giving this kind of variability in your predictions. However, you have implemented code in Python itself or the scikit-learn library, you can call mean squared error, the function from sklearn, and it can help you calculate the MSE for a given model. So basically, there was a very quick introduction to linear regression. Though there are different applications, but one thing remains common, that we are trying to predict the dependent variable whose nature or the type of dependent variable is numerical or continuous data. Some of the applications like predicting life expectancy based on these features like eating patterns, medications, disease, etc. You can predict housing price. We have already seen the example on that. We can predict the weight on different features like sex, weight, prior information about parents and all. And you can also predict the crop yield of crop based on different parameters like rainfall and all. And as I said, this is like very limited use case list. I'm sure people who are working with sales department, you have to make predictions. How much would be the sales? People who are working with call centers, you need to predict what would be the number of calls for next month. People who are working with marketing, you need to predict what would be the footfall in a given company or a mall. So there are different applications of regression models, but one thing is common across all these applications is that the dependent variable which we are trying to forecast is of continuous data type. So let's get moving to the next agenda for logistic regression. So at the time of the introduction to machine learning, we discussed there are two kinds of supervised learning techniques. One is regression and other one is classification. And the major differentiating factor between the two were that in regression, we held a dependent variable of continuous values, and in classification problems, we had a dependent variable of categorical types. So let's take an example of how we can do it. So here, let's take a use case where we have got some information about some customers, and the data set looks like this, that we have some customer ID or user IDs, gender of the customer or the user, his or her age, estimated salary every month, so you can think of in any one of the currency either INR or dollars, and whether this user purchased an SUV or not. So as I was saying earlier, the dependent variable here is 0 and 1. So it's a discrete value or categorical value, which we need to predict. And the features which we'll be using in the model are age and estimation. We have already discussed the linear regression, why we would need a logistic regression kind of algorithm. It would be a straightforward process that if I take purchase as a numerical value 0 and 1, and I take some input features like age and estimated salary. And you will be right in saying to some extent that this is a possibility of doing it. So there are two major problems coming if we follow this, and some of you can help me what may be the problems if I try using the linear regression for solving this kind of problem. But one limitation I can think of is that here I'm looking for an output which can give me some kind of probability that how likely I am to buy a product or service. So one thing that the limitation or the restriction with probability is that the probability term should be between 0 and 1. And 0 signifies that there is no probability or there is no likelihood of event happening. And 1 means that it's certain that the event will happen. There is no possibility that we can have probability values less than 0 or greater than 1. So if I'm fitting a linear model, taking the purchased column as my dependent variable, my values, because the linear regression has no such limitations, can pass these values beyond 1 or less than 0. So what I require is that I fit the model in the similar fashion like I did the linear regression, the equation I used earlier. Then I want that information would be coming from my features in the similar fashion. But what I want actually is that this y should be mapped to the values between 0 and 1. And given the limitation we have just talked about probability, that it should be between 0 and 1, it should not go beyond 1 and less than 0, I need to find ways if I can kind of force fit or kind of force this y value, which would be coming from this equation, and I force fit into values between 0 and 1. So to solve this problem, there was a function called sigmoid activation function, which would be extensively be used in our deep learning as well at different places. But logistic regression comes from this activation function itself, which is a function looks something like this, that output value would be 1 divided by 1 plus e to the power minus x. And x is not actually the one of the input, but any value we are giving it. And if you fit any value into this particular equation, it can convert any value between minus infinity to plus infinity. It will map it to between 0 and 1. If your value of x, which you are putting in here, I could have selected a different value, different name at least. But if you give the highly negative value, the output would be very, very close to 0. If this input is positive, then the output would be close to 1. If the value of x, the input here becomes 0, what would be the output? 1 by 2. Because any values power 0 is equal to 1, and 1 divided by 1 plus 1 would be equal to 1 by 2 or 0.5. So logistic regression is nothing but an extension of your linear regression itself, with one additional fact that you want to force fit your output between 0 and 1. And for that, you are using activation function called sigmoid activation function, or sometimes it's also been called logistic activation function, to do the same task. So this is an intuition behind your logistic regression, where you take values of your equation from intercept and different coefficients for your input, and you map these outputs between 0 and 1. So once we have understood that logistic regression is nothing but the extension of your linear regression only, with a restriction on the output being mapped between 0 and 1, we are shifting. Had we were fitting the regression equation, we would be having scenarios where the value would be going beyond 1 or less than 0. And to avoid this scenario, we fit in logistic regression with the help of sigmoid activation function, which looks like this. And if you see, as I was saying, when your value of your model go beyond, let's say this is R0. So all the values which are positive and greater than 0, the curve goes and tangential towards 1. And for all the values which are less than 0, it goes towards 0. And at the place of 0, the probability is 0.5. So it's a 50% probability if your output is very much close to 0 or it's 0. So sigmoid activation function is being used for that purpose. It can be used for multiple scenarios. One of the example we are taking is the example whether somebody will buy an SUV or not. But if you're trying to solve problems like somebody will say yes or no to a product or service, or whether something is true or false, or high-low, or any different categories. But logistic regression can easily be put in for multi-class classification problems. And basically, if I just give you a very quick introduction, how it works is that in multi-class classifications, it kind of does mapping that one class versus rest of the other classes. And then same analogy follows, that which class a particular event would be associated with. But end of the day, for whichever class or category the probability is highest, the model will predict that it should be belong to that particular class. Like MSC, we have a statistic or a parameter to evaluate how good your model is doing. To compare how good your model is doing, you have MSC, mean squared error, and that was a parameter to check that what is the difference between the actual value and the predicted value. And how we were doing it, we were taking the value which was actual, subtracting the predicted value, taking square of it, do it for all the examples, and divide it by number of training examples we have. And then it gives you some number. And I was also saying that this number is helpful in kind of comparing different models. So let's say you fit a model, I fit a model, and we compare MSC for both of them. Whichever model is giving me a lesser MSC, it is kind of an indication that probably your model is doing a better job in terms of prediction than mine. In a similar fashion, we needed a kind of a statistic to see how good your model is doing when your model is doing a classification problem. So here there are 4 categories that, let's say we have only 2 classes, good and bad. Actual values good and bad, and what your model is predicting good and bad. So 4 examples which belong to good category, and your model is also predicting them good category. So this type of events or examples are called true positives, because your model is doing correct prediction on positive examples. Another category, which is your actual value for those examples is bad, they belong to bad category, and your model is also predicting them bad. These are called true negatives. And these are correct predictions, because whatever the actual value is, your model is also predicting the same thing. However, there are 2 categories where your actual value was bad, but your model is predicting good. These kind of examples are called false positive, because your model is falsely predicting them these are good examples. And another category, or last category, is called false negative, where actual value were good and your model is predicting bad. So how do you learn, or how does your model say that which model is doing good job? So what we do is we calculate what is the percentage of values examples have been predicted correctly. These sections in blue, true positive and true negatives, these are the examples which your model has been able to predict correctly. And these 2 groups, false positive and false negative, are the incorrect predictions. So what we do is we just want to take what is the percentage of correct predictions, and this metric is also called confusion metric. let's say there are some examples out of which 65 examples were there where actually they were good category examples and your model is also predicting them as good class, good category examples. 44 are those where they belong to the bad category and your model is also predicting them bad. This is 44. And 8 are actual bad and prediction is good, and 4 are actually good and predicted bad. What you do is you sum up all the correct examples, 64 and 44, and divided it by all the examples in your data set, all correct and incorrect ones. And here you get 89%. So all you can say that your model is being able to predict 89% accurately. Or if you want to explain it to your business team and say that whenever I give you a prediction that 100 customers will churn and I give you a list of 100 customers, I can say with certainty that at least 89 will churn from them with some certainty. So because your model has given you 89% accuracy. So that's how it's been kind of communicated to business teams, that we are thinking that our model is 99% accurate and whatever prediction we are giving, we are very, very certain. But if your model accuracy is 70 or 60%, then when you give the predictions to a business team, you say that, okay, though we are giving you the predictions, but we are not very certain whether it'll work correctly or not. So this accuracy percentages in a similar fashion like we did for linear regression as MSC to identify how good the predictions are. Your accuracy percentage is another metric to see how close or how correct the predictions has been. So now we can see the implementation of logistic regression in Python. So first few lines, if you see, we are importing the libraries or the machine learning libraries which we require to do the data manipulations. We are importing the data, which is a CSV format, and this data is already available on your LMS. If you want to import, you can easily import from the LMS itself. Unlike the Boston dataset, which we were importing from the library itself, here we have got a flat file as social network ads.csv, and you can call a read_csv function of pandas library to import the data. So you are importing the data as dataset, and as I said, head showcase the top 5 rows of your data. So here we have only 5 columns. One is user ID, gender, age, and salary. And the last column is our dependent variable, which signifies whether a customer or a user bought the SUV or not. So it's 0 and 1, and 1 means the person bought. In the previous code, we used one convention of selecting X and Y. Here we are showcasing another way of selecting, that's called iLoc. So we are looking for the location, and this convention, if I go through what we are doing here, that this is the dataset. Within the dataset, we are specifying the locations. This colon means that we want all the rows, and as I was saying earlier that in Python the index start from 0. So what we are saying, we want column 2 and 3. So what we mean that this is 0, this is 1, this is 2 and 3. So we want as our input features 2 and 3 and the values. So it will be creating an array of these 2 columns. We could have used gender, but I will leave it to you that first we need to create the gender as a vector of 0 and 1. So you can create a function which will say, okay, if gender is equal to male, then 1, else 0. Or you can create dummy variables. There are function available in scikit-learn. So it's an exercise for you that this is the code already available, but I would encourage that if you can also include gender information into your model. The next line of code, why we are saying the dependent variable, is all the rows and column number 4. So column number 4 is your purchase information, whether a customer bought the SUV or not, and again the values to convert into a kind of list format. So we have specified 2 things. The 2 columns is the information about the input features or the information about the user in terms of how much money they make and what their age is, and information of Y, whether a customer bought the SUV or not. And the next line, we are doing the train and test split for the same stuff to evaluate whether the predictions being made by the model on the training dataset on which the model was learned is still doing the correct classification on the dataset or the test dataset which was not involved at the time of training. And this 0.25 means that we are selecting 25% of the data for test and remaining 75% for our train. What is the correct split of train and test? Normally it is correct to choose between something like 60-40 or 70-30. or 80-20. If your data set is big enough, then I think having 80-20 kind of split is good, or whatever. You can try these different combinations, but as a rule of thumb, most of the time I have seen people taking something like 60-40 or 70-30 kind of distribution between actual value and the predicted value. Now, there is one important thing for data pre-processing, and this selection which I have made for doing the data pre-processing, and some of you who come from the machine learning background will already know that how important it is to kind of scale your data. And what do I mean by scaling? That if you look at the data set which we are using for input, one is the age column and second one is the income column. Age can be somewhere between, let's say, 1 to 100 or 120 at max, and your income is in like some thousand and some 100,000 numbers. Both these values are on different scale. Scaling your data on, let's say, all the values between 0 and 1 will help me understand that what is the importance of each variable. For example, if you look at a regression equation and you see those coefficient B1, B2 for all the input features, these coefficients can give you kind of indication that how important a particular variable is. But this intuition will only be correct if all my features were on the same scale. If these features like age and salary, when they are on different scales, you will not be able to compare what these coefficients really mean, because they are two different scale your values come from. So it is always a good idea to have all your features on the same scale. There are multiple ways of doing it, and there are multiple type of scaling parameters. The simplest one is called min-max standardization, and what does it mean is that for a given column, let's say we are talking about age column, which is 1935-26, if I need to do min-max standardization, what do I mean is that I take the value it is, let's say 19, and minimum value here is, let's say 19, I have only these 5 values. So how it works is that this is the formula, this is the value, or how it's been presented, xi minus the minimum value of the column, so let's say age, divided by max of age minus minimum of range as well. But basically what this formula will do, if I do it for all the values in the age column, it will be converting all the values between 0 and 1. And there are other ways. I also said that there are normalization process, which is like you take the value minus the average value, divide by the standard deviation, if I call it correctly. So whichever method we apply, all I'm saying is that these values of age and salary should be brought to the same scale. So if I'm applying this min-max standardization, I'll apply to both my columns so that both these variables are on the same scale, and I should be able to use them in my model. And this is again a very important thing, that whenever you do standardization, you will be using this process that you fit the normalization or standard scalar on the trained data set, and you use the same learned standardization from the train on the test data set. But basically how it helps, that your data set on which your model is being trained, it will be converting the values between 0 and 1 based on the minimum and maximum values. If the test data set have different minimum and maximum values, it can have different value for the same number. So that's why the process is that we make our standardization fit on the training data set and use the same minimum and maximum value for test normalization as well. It gives the same scale for all the values, and for model predictions it's very helpful. In a similar fashion, like we called a linear regression object from scikit-learn in the previous example, in exact same way, we can call a logistic regression function from the scikit-learn. So it's a scikit-learn linear model, and we are importing logistic regression. Now we are fitting the logistic regression between X train and Y train the same way we did it earlier for the linear regression. And once it has been fit, we can do the prediction for test data set. We are also doing the same thing, that we are calling the function which was classifier for the logistic regression, and we are doing it on the X test data set. And here the default probability is 0.5. So what your algorithm is doing in the back end, for all the examples wherever the probability in X test became greater than 0.5, it was tagged as 1, and for all the examples where probability was less than or equal to 0.5, it was tagged as 0. And now we are calling this function called confusion matrix between y-test and y-pred. So we are comparing that what is the values of your true positive, true negative, false positive, and false negative. So this is the values, that these are the true positive, these are true negative, and these are the misclassification values. And if you want to calculate the accuracy, you can easily do it by 65 plus 24 divided by 65 plus 24 plus 8 plus 3. So all we are doing is we are trying to identify what is the percentage of correctly predicted numbers. And this is the code of section. So it can do the prediction. If you see what it has done, basically, if you look at the section that your regression model has fit this line, and you can see it's a straight line. And that is why in some of the text, logistic regression is also being called a linear classifier. And why it is called linear classifier? Because it is predominantly being made for fitting a linear equation. The logistic regression equation was y equal to a plus b1x1, b2x2, and all these coefficients and respective inputs. But the highest power of your inputs were 1, and you would already know that if it's a polynomial of power 1, it stands for a straight line. So that's why you can see a straight line. There are ways, some of you would argue that we can fit a nonlinear line with the help of logistic regression, but you would also concede that there are some tricks which we use for creating nonlinear lines through logistic regression. For example, you introduce higher order polynomials into your model so that the separation becomes nonlinear. These kind of algorithms are really helpful only solving the problems when the objects are linearly separable. When the separation between the objects is not linearly separable, these kind of algorithms are not very helpful. And we need to identify algorithms which can fit in nonlinear hypothesis or separation boundaries between different classes. So let's take a use case to understand that what are the simple scenarios where unsupervised learning can be used and how does it really work. So let's take an example that we have some housing data, and housing data in terms that what their locations are, and these white dots on the screen in the blue background showcase that where these homes are located. And the objective of education officer is that he needs to find a few locations where the schools can be set up. And the constraint is that students don't have to travel much. So given this constraint in mind, the officer needs to decide the location. There may be easily we can identify if we are not using any algorithm. So let's say if I know that I'm an officer, I need to open 3 schools in the locality and I know the information where the homes are located, I can easily see, okay, probably this is one location. I'm just highlighting it. And the constraint I also mentioned that students don't have to travel much. What I mean is that if you open the school here, then everybody of you would say that it's not a great location for a school given that it's far away from the population. So this is not the correct location. And from the perspective of identifying the home, probably these 3 from a human intervention or like some of you has been given the task without any algorithm, you can decide that probably these are the 3 locations. If you set up the school, most of the students would be traveling less to go to a school. So given this problem, we can easily see that we don't have a dependent variable as such, which is telling us whether it's the correct location or not. All we're doing is that we have a number of locations which we need to find schools for, and then we have home locations, and based on the distance of each home, we need to identify which will be the proper distance or proper locations of these schools. And another thing which is coming from the same logic that there are no predefined classes of these locations. And one more point if you would like to add, and some of you who have done the clustering or the segmentation job in your respective works, that these numbers, we say 3 or 4 or 5, it's not predefined. It is most of the time given by the business that how many clusters or segments they would be looking for. Though there are statistical ways of identifying that which is the best number of clusters should be, but basically most of the time it would be coming from somebody in the business that, okay, I see that, let's say I was working for one of the Indian telecom companies here quite a time back, and at that time their subscriber base was around 300 million customers. And imagine that if you're trying to create segments for this bigger population, and if you create 3 or 4 clusters, you can easily understand that it would be very difficult for marketing team or any product team to design products for such a big population. So though statistically it may look that, okay, 4 or 5 unique segments are there, but you end up creating a lot of small segments, and there may be a possibility that you will be creating 20 or 30 segments for such a big population. So my intent of saying this number, that we are trying to identify 3 locations within the population, has to be decided either by business or people like you who have knowledge about the data, as well as that what kind of business they are running and what is the final usage of this segmentation exercise. So let's see, one way of doing or selection of these school locations is like we have already doing it. If you identify that somebody looked at the homes and see the densities where the density is high and selected the home automatically. But there are algorithms also available to do the task, and I can give the name here itself. It's k-means algorithm. And so first we would like to understand that how does an algorithm work if it needs to identify which is the best location. So if you are looking at my screen, let's say our objective is that we need to identify 2 locations first, and we have some data and its scatter plot available, and we need to identify where the school should be so that the distance from home should be minimum, if that's our objective. So how we can do it, that let's say we randomly assign 2 points from the existing data set. And actually easiest way is that you randomly pick 2 numbers from your data set itself. And then what you do is you assign these 2 selected points as these are your cluster centroids. So this is the center of your selected population. And in the second step, so once you have initialized these 2 random points, then the next step is that you measure the distance of all the homes from the initial selected point. So let's say you do the distance of this home from this selected point and again from this. That for each house from these randomly initialized point, you measure the distance from the selected point or the initialized point and any home location and see which distance is minimum or which distance is less in comparison to the other from the selected initial point. So we can easily see that this distance is smaller than this distance, and this point would be assigned to this particular group. The first initialization step is initialize as many number of centroid, as many clusters you need. And in the second step, you do the cluster assignment. And in cluster assignment, how it's been done is that you measure the distance from these initialized points and see wherever the distance is minimum, and then assign this home to that particular segment or cluster. So this exercise has been done for each home. I'm just trying to show for a couple of them. And based on the distance, the assignment is complete. So this color also signifies what we have done is after measuring the distance for each home from the initial points, we have assigned these points to this cluster and these blue points to second cluster. And then once this assignment is complete, it moves the centroid. So what we'll be doing is it'll be taking the center of all the selected points and then it will move the centroid from the previous point to the next point based on the new assignment which has already been completed. And then what's been done is the same exercise which was done earlier in terms of cluster assignment, that we measure the distance of each home from the centroid. So distance from this centroid and wherever it's minimum, assign it to that particular cluster. And this process has been repeated again for both the centroid. And once the distance has been measured on the improved or changed centroid, again the assignment process has been started. So once you have moved and then measure the distance, and then assignment also changes like it was done in the previous step. And we continue this process till the time we have reached a location or a point where this change in assignment have stopped completely. So once we have reached this kind of place or this kind of scenario where as many time you measure the distance from the centroid to the different points, your centroid does not change. This exercise or this point is called that your model has converged, and at that point you can say, okay, these all group, there is one group of these points or these homes, so this is one cluster and second one is this cluster. So this is how k-means work. It has wide variety of applications. There is a function available in scikit-learn library. You can try implement it. The intent of showcasing you this example of unsupervised learning was that we will be having 2 algorithms which come from unsupervised learning section of machine learning. and these would be your restricted Boltzmann machines and autoencoders, which work on a similar methodology of unsupervised learning. So in a similar fashion, like we started discussing in the beginning, that where should be the location of these schools, we can use a k-means algorithm and initialize 3 points randomly and do this distance measure to each home and assign the homes to a cluster wherever the distance is minimum. And we continue this process of measuring the distance and assigning it to the cluster till the time these values have been converged. The most important task for any data scientist is not to remember which library is required or what are the codes. In my understanding, the most important thing which data scientists should remember is that once you've been given a business problem, first you should be able to understand that what kind of problem it is, whether it's a problem of supervised learning or it's an unsupervised learning. Given it's a supervised learning problem, whether it falls into the regression type or a logistic regression type, if you can make these decisions, then for implementing the algorithm, you will find a lot of help. In fact, scikit-learn would have initial codes for almost every algorithm. So you don't have to remember line of code and algorithms. All you should be able to do is once a problem is being given to you, you should be able to identify what kind of problem it is. Most of the time in unsupervised learning and specifically in k-means kind of models, we use this elbow method as an indicator or help you understand that what is probably a number we should start with for starting the final implementation of your model. So let me give you an intuition. How does it work? SSD stands for sum of squared errors. And what it means is actually, if I go back a little, that suppose you have identified these two clusters. So sum of squared error would be that you take the centroid and measure the distance for the points which are associated with this cluster. So you measure the distance for each point in the orange group and sum square all the distances, and the same exercise being done for the blue points. And whatever the total number comes in after doing this exercise, you will be getting what is the total number of squared errors. And if you have two clusters, you would have some number. And just for intuition, I'm saying that this total sum of a square is coming as 100. And that's only for intuition and example. I'm taking this number to help you. Let's say there was one more cluster somebody identified here. And all these 3 points, though it's blue in color, but I'm saying all these 3 points belong to this particular segment. And rest of these points remained the same as it was previously. And as we saw with two clusters, our sum of a square was coming as 100. When we have 3, you can see that these points are a bit far off from this particular cluster. So if I'll be doing it with 3 clusters, this distance would be a bit less, given that now I have a point which is closer to these points. And whatever error or distance these 3 points were adding, it would be a bit less given the cluster was here. And let's say this distance goes down to 95. I'm just making up some numbers. So probably what it's telling me that sum of squared is going down, and probably I'm finding clusters which are closer or more closer to the actual data points. And as you would know that if I'll be increasing the number of clusters in the population, this distance would be going down hopefully. And this distance can go up to 0. And at what point this distance can go up to 0? When every point become a cluster itself. So if let's say I have 20 data points there, and I assign that every point is a cluster in itself, then just measuring the distance from the point, which would be 0, and overall SSD will become 0. So it may start from a very high number, but it will be reducing with each cluster point or cluster you will be adding to your data. So this line, which is sometimes being called the elbow method, what it's actually showing you that when you had one cluster, this was the distance. So if you had one cluster only anywhere in the population and you do some of the squared distances, this was the distance. When you had 2 clusters, this was the distance. When you had 3, these were the distance. When you had 4, this was the distance. But when you had 5, the sum of squared error did not reduce much. So if you see, it's like very less. And after that, even though you keep on adding different clusters, the sum of squared errors is not going down. So as I was saying, this process or this method is kind of indicative method, and it gives you an intuition that if I have done it, my cluster analysis with different number of clusters, and I'm measuring the sum of squared errors for given number of clusters, and I see that after 4, the sum of squared error is not going down, it gives me an intuition that probably I have found clusters which are more or less coherent and the population is not very much away from the centroid. From the point, you can make it an assumption that probably 4 clusters is a good idea for my given population. But as I also mentioned, that it is just an indicative process. It's a good starting point, but you need to see that how the distribution of your clusters look like, whether they solve the business problem you're trying to solve or not, and if not, that whether you need to further divide the clusters which your initial model has identified. And here we'll be taking very quick introduction to a third type of learning, which is called reinforcement learning. What it actually is, we have seen from the 2 learning types, the supervised learning and unsupervised learning. The first one was that we were trying to predict some dependent variable. In the second one, we are trying to identify some kind of structure in the data set, or if I put it into other words, that we are trying to identify some kind of coherent groups in the population. Third one is reinforcement learning, and it's basically that an object or a system learns from the environment, and there is no right or wrong answer given to the system explicitly or in the beginning itself, like in the case of supervised learning. Here, the object would be moving in the environment, and an example, that self-flying helicopters, where they fly on its own and they take the decision that what is the wind speed and what is the pressure around it, and they correct their procedure accordingly, and the objective they need to achieve is that they need to fly for a longer period of time. So here we are given an example. Let's say we have a robotic dog and somebody needs to train it to take correct decisions, and correct things would be that it walking on the path where people needs to walk, and it's not going down from the path, and if some task is being given, it's working correctly. So there are 2 components of reinforcement learning, which is called reward and penalty. If the object or the system does the correct thing, it receives some reward in terms of mathematical things. Obviously, we will be providing everything in terms of mathematical numbers. And if it does the wrong thing, it receives the penalty. And basis this thing, it will keep on taking its decisions. So like a dog, if it's walking correctly, it receives the points. Like ball is being thrown, if the robotic dogs go and pick it up, it's a reward point. If it doesn't do the correct thing, it receives a penalty. So most of all these reinforcement learning agents working in a similar fashion. Some of you who are interested in implementing it, there is an algorithm called DeepQ. It's an algorithm where you can design your own system and you can assign what are the rewards and penalties. Similar fashion, reinforcement learning is also interacting with the space, as I mentioned. So self-driving car is also one of the examples, which would be receiving rewards and penalties based on whether it's running on the track, taking the right turns and moving at the correct speed, maintaining distance from other cars which are running. So reinforcement learning has a huge implementation or requirement for self-driving cars, or some of the components of it, not all. Some of the components also in self-driving car are supervised learning, for the point that car needs to understand what the objects are in front of it and all other objects identification. So what are the real limitations of machine learning, given that we already have all 3 types of algorithms, supervised, unsupervised, and reinforcement learning algorithm already available? Then why we want a new architecture or new type of algorithms for our artificial intelligence systems? First and foremost is the dimensions. And when I say dimension, it's like the type of data we get from a lot of sources. Let's say we receive images, which is grid-like image. So where the pixels and what is the strength of pixels in the image. Natural language processing, so language data comes in a different length, and the work is also different in the sense that suppose you need to design a machine learning algorithm which can do language translation. And if you conceptualize this idea of language translation from a machine learning algorithm perspective, your inputs become a sequence of words and your output is also sequence of word. And some of you who are working in machine learning algorithm, try thinking that whether we have any algorithm currently available, like logistic regression or decision tree, which can help me even fit the algorithm or fit the problem. Leave aside how good the accuracy would be and all, but these problems which come from a different type of data source and we trying to solve a different kind of problem, like language translation or chatbot kind of problem where you give a sequence and it returns you a sequence. So these kind of architecture is already not available in machine learning. So that is one of the reasons that we need to identify some algorithms which can deal with such data sets like images and languages. And second, it can also fit different kind of models, which are not only for predicting or classifying, but also give you some kind of values like sequence I take an example of. So that is one of the reasons. First, we are looking for a different type of architecture for solving such problems. Then second problem, which machine learning algorithms are not very good in dealing, is the dimensionality. So we would have seen, and with a size of, let's say, 1,000 variables and let's say 100,000 rows and 1,000 columns, probably you can still fit some of the machine learning algorithms on top of it. But given the kind of problems we are dealing with, like images, every image, let's say it's 200 by 200, means 200 pixel by 200 pixel, and it's a colored image. It means there are 3 channels. We'll be discussing in details, but basically all I'm trying to say that a simple image of 200 by 200 pixel will be giving you, if you do the maths, 200 multiplied by 200 and the image. So let's say this is your image and it's 200 by 200 because every image is kind of a matrix only. And if it's a colored image, actually colored image are being represented in a system through 3 channels, red, green and blue. So there will be 3 such grids, but one top of the other. So number of pixels you need to have to represent your image in the system or in your algorithm would be 200 by 200 by 3. And then you calculate how many features it would be. If my math is correct, it should be like 120,000 features. So even a simple image of such small dimensions, you end up getting 120,000 features. And plus, if you're really working on a complex problem solving in terms of, let's say, an object identification in the images, there may be 5 or 6 objects which you need to identify, and you're dealing with, let's say, 100,000 images. Then your scale of data becomes so huge for any machine learning algorithm to easily handle it. And your machine learning algorithms fail in terms of getting any interesting results out of it. So coming to solution part, that we need an architecture which can not only read such data in terms of images, but it is capable enough of dealing with such huge dimensions of data. So this is the second benefit which comes from the deep learning algorithms, and we'll be discussing how do they manage such high dimensional data when we go and talk about different architectures. And third, and the most important reason that we will be looking for a different kind of model structure or different kind of algorithm is for identifying the features. So let me spend a couple of minutes on this idea. What do we mean identifying features? So in machine learning algorithms, we as data scientists spend a lot of time in kind of curating the important features. Either first you'll be scaling the features, and after scaling you'll be creating the interaction variables, then you'll be creating, if the separator is not very clear, then you need to introduce high dimensional data. Let's say it's your data point. And if you see that line you're fitting is not separating clearly, then some of you would be trying the higher order polynomials of your input features. So all such things which not only difficult to come up, there is a lot of trial and error that which kind of transformation and which kind of variable creation. So what kind of variable will really work for classification problem? That's first thing. And second is, if you're working on higher order polynomials, what is the correct order of polynomial I need to create it? And just to give you the scale of it, let's say you are dealing with only 100 features and you need to create second order polynomial with interaction of all these 100 features, then you will end up getting around 5,000 features from the second order polynomial only. If you want to get third order polynomial like cube variables or the interaction of 3 variables together, then these 100 variables will come around 170,000 features. So this creation of features is very, very difficult. And given that in our images, if you look at the image which is in front of you, if we go and start creating these features on our own, and our objective, let's say, to identify a television in the image, suppose, which I'm highlighting here, and we have some pictures where we need to identify, even though you have created those features manually, and some of you who are working in the field of computer science for quite some time would know that earlier we used to use features like SIFT, SIFT, HAR features and HOG features, but these are like kind of static features for a given object. But we may argue that this television is there in this picture here, but in other picture it can be somewhere else. So the feature which I'm identifying, it has to be spatial indifference, that it can be anywhere in the image. And same goes for language, that if you're dealing with language data, it should be not only able to understand the meaning of word or how does the word fit into the sentence, but it should also be able to understand that what is the context of each word. But these word embeddings, neural network, help you understand it, what are the related word to a given word. And from that you make predictions. So these broad problems of machine learning algorithms, one is they are not being able to play with or deal with different type of data like images and natural language. Second is the dimensional problem, if the dimensionality goes in like 100,000 features and all. And third is this feature creation on its own. So these are the three basic reasons that one of you or all of you would be interested in going to one of the deep learning architecture for solving such problems. And fourth, if I may add it, that all the deep learning architectures, given that we are putting a lot of computational powers in them, they end up giving you a better accuracy both for classification and regression problems. So that's the fourth benefit. And how does it really work? There are different stages in a deep learning, and why they are called deep, because it's not just input and output like we have seen in regression, that you have a y and x is some kind of linear equation. Here we have different intermediate field like we are seeing in the screen, like these are, but there are a lot of intermediary field for doing such complex calculations, so that all these features which I mentioned, that suppose you need to identify a television, all such features get calculated at different stages, one after the other. And final stage, you have very, very refined features, not only for image, we are taking the image classification, but any problem we are trying to solve. Through the multiple stages, your model would be able to learn these intelligent features which are really important for your classification or regression or any such problem which you are trying to solve. So these were the few benefits for deep learning, and these are actually the broad reasons that somebody would be interested in learning the deep learning algorithms, and some of them we would be. If you can see the screen now, that the implementation of deep learning has been into almost all the areas, either images and the language or even the structured data, which we have been working using machine learning algorithms. There is a huge implementation of neural networks now in dealing with structured data as well, for predicting like churn or who will be buying the product or not. Even these kind of algorithms are moving towards deep learning. So though you would have seen a lot of implementation from images or language only, but the application of deep learning is now happening in almost every field. And there are different architectures which are being implemented for different such problems. So if you see, some of the applications are already here, like automatic machine translation, object classification in photographs. Then there is a library, or there is an API being introduced by TensorFlow just a couple of months back, which is called object detection. So object detection API, it's a very strong API. I have used it already, and it can help you classify almost 90 objects in an image. And it's so powerful that its accuracy is almost 99%, and sometimes it's outperform even the human visual powers. We have handwriting generation, so there are new kind of architectures which is not in the scope, but there is a new kind of algorithms called generative adversarial models or networks, which is called GAN, G-A-N. And these networks are really powerful in generating new data set. And what I mean is that you give some images, let's say you have some 1,000 images, and you want to generate fake images or images from this data which looks similar to the images you already have. It means you can generate your own data from the existing data set. So we have a separate algorithm, and image captioning is there, that you can embed different models together for generating text from the image, that what's happening in the image. You could have seen the image captioning. And game playing we have already seen, automatic car drive and all. So there are a lot of applications. This is just a small list of applications. One small example is Google Lens. You can try installing and see how does it work. It can read text from the image itself. It can identify different objects. So basically there are huge implementation of deep learning modules and algorithms in different spheres of business problems and different kind of data and different kind of business problems. So some of them are here. What these tensors are, So these tensors are nothing but array of numbers. So these are just multidimensional arrays where the numbers are being represented in terms of matrix. As we recall that this is a matrix, 3 and 3, 6 and 4, it's by 6 by 4 matrix. We can see this is just a vector. And their rank represents that how many dimensions are. So if you look at the vector, it's just one dimensional tensor. There are two dimensions, one this, second is this. So it's second dimensional. And it's a three-dimensional array. So it's like 3 dimensions here. And people who are familiar with multidimensional arrays, it should be fine. And if not, then probably this example can help you visualize that what we are talking about. So number 7, which is just a scalar in matrix introduction or matrix computations, you would have heard that a single number is called scalar, and here its rank is 0, it's just a number. Any vector of any length would be called of rank 1. This is one-dimensional array. This is a two-dimensional array, and most of the data would be coming in two-dimensional array shape. Like, just to give you an intuition that you can think of these as different columns: age, gender, income, city, and all those different numbers. So you can think of these columns, and these are rows. So whatever the data we have been dealing with, structured data form, you can think of for the structured data. So this is a two-dimensional data, or we can call it also data of rank 2. Also the image data, which comes in this kind of format. So image has also been either in two-dimensional or three-dimensional. But basically, if you look at the image, there are some pixel values on the image. And based on those pixel values, the image comes up on the screen. So image is also a two-dimensional array if it's a black and white image. However, if it's a colored image, and I also mentioned, I think just some time back, that there are 3 channels or 3 colors which make different kind of colors based on the combination of 3 channels. So basically, a color image look like this, that there would be 3 arrays of numbers for 3 different colors. So RGB, red, green, and blue. And there would be pixel intensity on each one of those, something like which you're presenting here. And based on the pixel intensity of all these 3, on top of it, different colors would be coming. So, combination of these 3 pixels for 3 channels would be generating different kind of colors on the screen. If you have this kind of data, it's called rank 3 because there are 3 dimensions. Your data can be of more than 3 dimensions, but you would know that it will be very difficult to visualize. So this is the basic understanding or introduction to what these tensors are and how do we mean by different rank and dimensions of a tensor. So let's get started. So one thing is the takeaway from the point we have discussed in a couple of slides is that data has to be converted or data has to be represented in terms of tensors before we take any kind of calculations or mathematical computations in TensorFlow. Shape, again, we have seen that if it's a number only, its dimension would be 0. But the shape of a vector, if there would be different functions, and we have already seen in the previous example, if you recall, when we were running the regression and logistic regression, I ran this shape function. So x.shape and y.shape when I was running, it was giving me a number of rows and columns. When I ran it for y variable, it just gave me number of rows. So it's in the similar fashion, it's just a one-dimensional array and there are 5 objects in it. So the shape is 5. For a two-dimensional array, that matrix have a shape of number of rows and columns. So this is a shape of this and this. And for a three-dimensional, it will be like rows, columns, and the depth of the multidimensional array. So there will be 5, 4, and 3. So that's how you need to read it. So 5 in this direction, 5 in this direction, 4 in this direction, and 3 in the depth. So every data point, and why it is really important and why I'm spending good amount of time on this, that even today, most of the time, we end up making a lot of mistakes in terms of defining the dimensions of the data. And you will see that when you really design an architecture for deep learning, you will be mentioning a lot of points like what is the dimension of your inputs, what is the dimension of output, what is the dimension of different weights. And there would be a huge amount of weights. Actually, this is the only big problem in TensorFlow or any other deep learning, is that you still need to define the weight dimensions on your own. And most of the time problem comes from this section itself. When you go and design your own deep learning architecture, you need to be really cautious about the dimensions. So there are 2 sections in TensorFlow library, which is nothing but TensorFlow is an open source library, at least for now, from Google. It started from the Google Brain project, and now it's available to all of us free of cost. There are two sections of TensorFlow. One is the tensor, which we have already discussed, that we need to convert our data in terms of numerical representation of every data. And then second is flow. And people who come from the programming background will already know that what is a lazy evaluation, but for others who are new. So what do we mean on an intuitive level? That we give our inputs. So I'll give you some names here. So X is our input features. W are weights associated with it. Matmul is matrix multiplication. So you take X and W, do the matrix multiplication, add bias term. So we are taking the bias and adding it. And then we are applying one of the activation functions. Whatever the output comes from this, you apply the activation function called ReLU. So in TensorFlow, how it would be running, that you will not be getting output for each of these inputs till the time you don't explicitly call it. So how it works in TensorFlow is that you design the entire flow of your algorithm or your program, and only you run this last component, which is the ReLU. And what will happen is that when you run this command or just ReLU operation, it will go back and automatically calculate all of them in the backend. You can see the output whenever you want, but that's how it works, that you don't have to run it individually. You just run the last part and it goes back and run the intermediary sections of your functions. As I said, there are two sections within the TensorFlow, which we already seen, the tensor and flow. And within flow, it would be done in two sections. One, you have to define the graph. So you will be defining that what all functions and what all calculations you require in the program. And then you have to explicitly run it. Once you have installed TensorFlow in your system, calling the TensorFlow library is as simple or as we have done for other libraries like Pandas or NumPy. It remains absolutely the same way, that you import TensorFlow as TF, and it's just the name. You can give any name instead of TF. And I'm running this code on 2.7. If somebody is still working on 2.7, it should be fine. There are three types of data objects or data types in TensorFlow. And all the programs or everything you will be written in TensorFlow from now on would be one of its type data. So you will be explicitly telling the program that I'm writing this whatever line of code and whatever assignment function you will be using for one type of these data. There are three basic types, and these would be used extensively across your programs. So first one is a call constant. And constant in TensorFlow is absolutely the same, whatever our understanding has been of a constant. That constant is a value which doesn't change. Whatever value we assign to a constant, it remains same. For example, if I say a equal to 5, and if I think that it's a constant, then the value of a will always remain 5. It doesn't change at all. So the same convention remain in TensorFlow, that if I have specified a data object as constant, its value would be same across the program and it will not be changing. And I can assign constant as a string or a number or an integer. It can be any of the types. So let's see a hello world program in TensorFlow, that how you can run it. That hello world, I'm assigning hello as tf.constant. This is the way, because I have installed or I have imported TensorFlow as TF now. Once whatever name you assign it as, then you would be calling all the functions with the same abbreviation itself. So here I'm saying that tf.constant, and I'm giving the word as hello world. And though it has been in all our programs till now in Python that once I have assigned a value to some object, if I want to run it, it should give me the value. But here you see it's not giving you any output. My expectation was it should be giving me hello world, but it's giving me tf.tensor, constant shape, d type is string, but not giving the actual value which I wanted. And why it is not giving? Because there are two components of a TensorFlow program. One was that you need to design or set up the graph, and second is running it. So in TensorFlow, everything has to be run within a session. So this session is the running part. So we have to explicitly tell the program that run this command or run this object within TensorFlow session. And this is one of the ways of writing a TensorFlow session command with tf.session, and s has to be capital letter, as ses, and then you have to use actually this command, ses.run, and then you say what you want to run it for. So if you see, I'm calling an output by running ses.run, and then I'm calling this hello constant, and then I'm asking that print the output. And if you do it now, it would be giving me the output which I expected earlier. So this convention will remain same across all the programs from now on for TensorFlow, that whenever you have done the assignment part of it, you have to run this function or any line of code within a TensorFlow session only. And one of the ways of doing is this. So there are different type of data, like float32 is decimal value, there would be int and again int2, and these 3264 is like the bit shape of your data being designed. And people who come from programming would know that how many bits being taken to define your number in the backend. From that perspective, there are 2 or 3 types which we'll be working with extensively. One is the float, and most of the time we'll be using float32, and the other one is int, which we will be using for specifying integers. But for constants, the float32 is the default type of data. Till the time we go ahead and explicitly mention that we want to specify constant as int, then you have to tell that the constant which I'm specifying, let's say node1, is tf.constant, and I'm specifying what this value is, and I'm specifying whether it's float type. And if I've just given the decimal here, it's easy to understand for the algorithm that it's a float32 kind of data. And as in the previous command, we saw that when we run this code, we don't get the output of node 1, which is we were expecting 3, and for node 2, we were expecting 4. But we get this information that this is just a tensor and what are the type of data each constant has. And like we run the session in the previous example, I was saying there was one of the ways where we said that with TensorFlow session as some name and then run it. We can define it in another way, like we can say sesh equal to tf.session, and then I can run whatever command I want to do. So here I can do it that print sesh.run node 1 and node 2 and sesh close. This one is very important, that if we are specifying our session in this particular fashion, where we are saying sesh equal to sesh.session, then we have to explicitly say that now close the session. If you don't close the session, it would be running, and there may be some issues from the point that suppose you have run node 1 multiple times in your code. So there may be a possibility that it may pick up the wrong value. So if you're specifying your session in this particular way, you need to say sesh.close. And if you're running from the previous way like we did here with TensorFlow session, so in this particular fashion, if you run the command with TensorFlow session, whenever the code is done, it closes automatically. So you don't have to worry about that you have to run this command of sesh.close. So there are 2 ways you can use TensorFlow.sessions. Here I wanted to show you that there are very simple calculations which you can do. So here I'm showcasing this flow understanding. When I presented the first slide on TensorFlow, I was saying there are 2 components, tensor and flow. So tensors you can define like this as a constant. So this is one of the ways of defining those tensors. And then I am doing some kind of mathematical computation. So let's say I have said that I want to assign C as A multiplication of B. So this is my formula or function which I need to achieve. As all of you know that we will be doing that lot of computations in our deep learning program. But here I'm showcasing very simple one, that if I need to multiply A with B, though it remains same as it would have been earlier, that it doesn't give me any output. So if I run C, I don't have to recall like in the previous function. If I just go back a bit, here if you see I'm running my node 1 and node 2, which is nothing but the assignment of constant. But what I'm trying to show here from the flow perspective, which I mentioned in the slide, that when you have designed a program something like this, where you specify A and B, and then you also specify what is the mathematical relationship between A and B and what is the resultant value. All you do is you run the final value or final step in your overall program. And here C is the final step. So I only run C, and what it does in the backend is that it will be running C and say, okay, C is the output of A and B, and then it'll go back one way further and say, okay, what A and B, and do running the program accordingly. So here if I call only C and I run C, it will be calling A and B accordingly and give me the final output, which is 4 multiplied by 6, which were the constant values of A and B. So this is a very small and toy example of how the flow works. And had there been multiple functions after C, you would be doing like D is multiplication of C multiplied by something number. So you just need to run D and all the other functions will be running automatically. So the second type is called a placeholder. And we will be using extensively this kind of data type. And I really like this one line is available. I have copy pasted from TensorFlow website itself. and it says that the placeholder is a promise to provide value later. And the most simple and easier example is that most of your features and label values like your X and Y's would be initiated in your TensorFlow program as placeholder values. And what it does it that you can assign any value. Let's say you have assigned A is equal to tf.placeholder. So we are saying it's a placeholder type of data, and the type of data is float32. So whatever value I'll be providing in future for A, these would be float values. B is, I am mentioning, that will be float type 32, and then I can assign a operation, a mathematical operation. One more thing I would like to add, that placeholder objects will always be coming with another thing called feed dict or feed dictionary. So whenever we have a placeholder object, we will be giving all the final values with the help of a dictionary. So people who know what a dictionary type is in Python would know that we can assign key and value in this particular format. So here it's been represented in Python with curly brackets, and what we are actually saying is that there is a dictionary where A is equal to 1, 7, and 6. And if you recall, this kind of representation is a list. So A is a list of 1, 7, and 6, and B is a list of 3, 20, and 2. You can think of this that you are assigning your X is equal to 1, 7, and 6, and Y is equal to 3, 20, and 2. And this is the same way you will be designing your input as well as output features of your model. And when you run it, obviously you get this output: 1 plus 3 equal to 4, 7 plus 20 is equal to 27, 6 plus 2 is equal to 8. The benefit of this kind of implementation is that your data on which you are developing your model, its shape and size may change anytime. So for example, if I take a very simplistic approach, that initially when you run the model, you only had 3 data points, but tomorrow you have got 2 more data points for your information. So let's say you have added 2 more information for your data, and this is the new data set. And when you run it, so basically you don't have to change your code on top. You can mention and change the assignment in your feed dictionary, and your operation can be changed accordingly. And that would be very, very helpful when you'll be running bigger programs where your X values and Y values, you may be getting, you're changing the number of columns, number of rows in your data set, and trying if there is some kind of problem with your data, which you need to change every time. Another thing I wanted to show you, that let's say, like in the previous example, that apart from this noder add A plus B, if I assign any other calculation, like I'm saying multiply 5, and this is the output coming from this previous operation, to multiply it by 5. So I don't have to run the intermediate functions. All I can do is I can run the last function. And here I'm kind of giving the inputs of 2-dimensional data. So if you see, it's like 3 rows and 3 columns kind of data. It will still be doing its job accordingly. Third, and another most important variable, comes from the TensorFlow called TensorFlow variable. And if you see that this is a capital V, and that sometime you may make mistake in writing it as small v, given that constant and placeholder start with the lowercase words or letters. Now first discuss and understand what a variable may. And its definition, again, one-liner for variable from the website itself, is that variable allows us to add trainable parameters to a graph. What basically it's trying to say is that tf.variable type of data is the kind of values which you can initially assign anything, but during the program you can change the values for your purpose. And I'll be telling you why we need it, and that's the important stuff for your learning process. So from the syntactical point of view, you can assign, just like we did for a placeholder or a constant in TensorFlow, we can assign a value. Let's say we are assigning it w1, and the w1 is, you can think, weight 1. We are assigning tf.variable, and we are saying the value is 0.5, and it's tf.float type. This is the way of assignment, but there is one more syntactical line. This is required to run your code, that every time you are assigning a variable type data in your code, you have to mention this line, which is tf dot global variable initializer. If you don't mention this line, your program will not be assigning value, which is 0.5, to W1. And in fact, if you run it, let me comment it and run it without it, it'll be giving you a huge error and saying init is not defined. And even though you change it something else, it'll be giving you a huge error, because for assigning the values, you need to run this particular line of code. When you run this, what it does, it initialize this tf.variable type of data and do the assignment of 0.5 to W1. So this is only from the syntactical way that whatever number of tf.variable type of assignment you have done in your program, end of the program you just run this line so that the assignment is complete for all the variable types, and then you can use it the way you wanted it earlier. So this is a very simple intuition. So let's take an example from regression. My intent here is that I need to explain it to you, the concepts behind the cost function and the optimization. But let's say this is our x, this is y, a very simplistic approach, and this is our actual data. Hopefully you can see my screen. So let me change the color. So this is the data we have. And what is the best regression line? Which goes through the data set or does the good prediction. Because you know that there can be n number of lines which can pass through. I can use this line, or there can be this line, or there can be infinite number of lines which can go through. So how does your algorithm decides and say that what is the best line for your equation, and whatever output which came yesterday after this scikit-learn, let's say it was this, I'm just making up some numbers, that intercept value is 0.2 and the coefficient of x is 0.3, and this is the equation of line. And probably, let me highlight this another time, let's say this was the green one is the line which your model has selected. But you would agree with me that your model has tried different lines and after that it has selected. So how does this process happens? And actually this is core to all our algorithms, either machine learning, deep learning, or whatever. But this process of one thing called cost and second thing called optimization, these two things are common across all your algorithms, and if you understand this part, then all you need to do is that you just need to see what are the variation between these two things for different algorithms. This thing does not change for any one of the algorithms. So how does it really work? So let me first talk about only cost. So what it does, let's say this is the green one I'm hovering over, this is the line, and I need to understand what is the cost for it. So what it does, it will say, okay, this is the predicted value for this, and this is the actual value. The total cost for this particular line is square sum of all these distances. So whatever the distance was here, all these distances I take, and I take sigma of all the distances, and distances are nothing, y actual minus, let me say it, I and yi hat for a given line. So we have understood how do we calculate the cost, and our objective is that whichever lines we are fitting in, for all the lines, all we have to do is you compute the cost, and whichever line is giving me the least value for this cost, I say this is the final line, and you give the slope and intercept for that particular line. So now we have understood that how the cost is being calculated, but there is one thing still being not clear, that how does a system identifies that which is the line, and how does it initially start that line. So as I was saying, initially this is the data, all we know is that this is our data is, and we need to find a regression line for it. And just to mention that this process remains same for both classification, regression, whether multiple class, single class, and the way we will be calculating cost and optimization, that would be different, but the process remain exact same. Let me write what we were looking for. Cost and optimization. So cost we understood from this toy example, that how do we calculate cost. But we were at a discussion on tf.variable and what this tf.variable is and why it is important. So let me come back to it, that why tf.variable is important. So we know that we have just one variable, and our equation is going to be y is equal to intercept some coefficient plus the slope multiplied by x. And as of now, we don't know what is the value of intercept or slope would be. So how this process has been designed for any algorithm, I'm mentioning it, I'm giving emphasis that any algorithm, because it will be same across any one of the algorithm. So how it's been done initially is, let's say I'm representing A for brevity and for B, the slope. So how we initially do it, that we assign any value A as tf dot variable, because I know this its value can change, tf dot variable, and let's say initially I assign it to 0. There would be different intelligent ways of designing how do we put the initial value, but let's say I have initially said that both the values of tf dot variable is again 0. So you will agree with me, if I have A equal to 0 and B equal to 0, then the predicted line from this equation would be what? My x-axis, because both the values are 0. So y is always 0 only on this particular line. So what I'll do, that once I have initialized these values, I'll calculate the distance for this line. So basically the prediction for my model is the bottom line, this x-axis. This is the prediction coming from A is equal to 0 and B equal to 0. And then I calculate the distance from my line and I take distance for all of them. For all the points, I'll take the distances and I do calculation for my cost. That actual values are these points and predicted values are all these 0 values, and I take the distance for each point and sum of squared errors I do, and whatever the cost I have got, this has been fixed. Now in the next iteration, because that will be iterative process, that I'll be changing my values of A and B, and I'll keep on doing till the time I reach to a line where the distance between the predicted values and actual values are limited. I'll be talking about how these values are changed. So I have done the cost, and let's say at this particular instance, the sum of distance errors or square error is 100. So distance from each one of the point from the line and square and sum is coming 100. So next step, what I do is I change the value of A and B, because of these are variable types. I can change the value. So what I say, in the next iteration, instead of having the value of A is equal to 0 and B equal to 0, assign them A is equal to previous value plus 1 and B is equal to, again updated by positive 1. Now the A's value is 1 and B's value is 1, then probably this line would be something like change the values of my A and B, and now it's a bit of positive, then probably it would look something like this, because now A, let's say this is the distance of 1, and again X value is changing by 1 and you are adding this up. So now instead of having this line, I end up getting a new line. This process of changing my weight in a direction where the cost is reducing. So let's say for this particular line where A is equal to 0 and B equal to 0, cost was 100. But when I updated values of A to 1 and B to 1, cost has reduced to, let's say, 90. So what do I mean is that once we have identified that we have updated the value of A and B from 0 to 1, the cost has gone down. This process is called optimization. So these two terms, cost and optimization, they work hand in hand, and the process is that you take any initial values of A and B. I'm initializing with zeros, and then you compute the cost between the difference, and then you update it in the direction so that cost can be reducing. I'll be going in details that how does model understand that which direction the weight needs to be changed, whether it needs to be add 1 or subtract 1 or add 2 or add 5. That will be going in details. But from the intuition perspective, this process of updating your weight in the direction so that your cost is minimized in each direction is called optimization. And we'll be going in different directions to understand how does model understand. Once we have understood the concept of loss, and it's one of the most important concept, I'm saying it again. So let's have a look. We are first showcasing that how you can set up a linear equation in the model. So what we are doing is, suppose this is the equation y equal to b plus wx, we need to design in a model. So we are initializing w and b as the variable type, and the values are 0.3 for w and minus 0.9 for b, and then x is a placeholder. So like we said, we will be providing the value of our x later on. We have decided the linear equation is wx plus b. This is the line of code, global variable initializer, to initialize the variable type objects into the model. I initialize my session as df.session. and then I run init so that the values of variable types can be initialized, and then I run the linear model as sys.run. I'm running the linear model with a feed dict. So I'm not mentioning feed dict. If I go back, I mentioned that your code automatically understand that all the values between this curly bracket are dictionary type. And now what your model is doing is it's taking 1, multiplying it by w, which is 0.3, plus minus 0.9, which is the b value, and it's been done for all the values of x. So this is a very crude way of designing the model. But here, if you see, we are not doing any weight optimization. All we are doing, whatever the value were there, we have initialized, they remain same, and whatever the output came, we have taken as it is. For addition, we can use tf.add. For subtraction, add tf.subtract. And for multiplication, multiply is tf.multiply. And one more important thing is for matrix multiplication, we will be calling a function called matmul. tf.matmul. So that stands for matrix multiplication. Though it's not very important, but I've just put in there to explain it to you that sometimes your data is not being defined in the way you want it. So tf.cast is a function in which you can use to convert your data. So if you see that this is a float type because I'm taking 2.0, and if I need to convert it to the integer type, I can use this cast function. I think cast is also available in SQL as well. So tf.cast, and it can convert it to the integer type. This one is for divide. So we understood some of the basic building blocks of TensorFlow, and these were constant, placeholder, and variable. These activation functions are kind of mapping functions between input and output, and here the input and output are not those input features and output levels, but all this input and output is that if you provide a number to a function, it kind of does some mathematical computation on top of it and returns some value. It has been used in numerous ways, numerous places, and some of these, especially the sigmoid, 10H, ReLU, and softmax, the bottom 4, you will be using extensively throughout this course. However, these activation functions are nothing to be scared of. These are just mathematical functions which transform a mathematical value in some other value. That's why they are called transformation functions as well. So first one is called linear identity, and basically it's nothing. You can think of it as a no function being applied, though you will be hearing that linear activation function is used. And basically what does it do is that whatever value you give to the function, if you give function a value of 0, it will return 0. If you give 2, it returns 2. If you give n, it returns n. So this kind of line you can think of that whatever value you give on x, the same value of y is being returned. So it's a kind of identity function also being called. This has been used in the output layer of a neural network where we need to predict some kind of numerical value. Let's say regression kind of problem we are going to solve, and we don't have to give the prediction in terms of probabilities. We just need to predict some real numbers. Then we can use in the output layer this kind of activation function. Or you can also think we are not applying any activation function, as simple as it is. But in some text, it's been called a linear activation function. So that's why it's just good to know. Second type is called a threshold function or threshold unit function or a unit step. What does it really do is it's a kind of threshold function. And what it does it that if the value of x is beyond some value, here we are given example of if 0 is greater than x, then 0, 1 if x is greater than 0. So that's like some threshold we have put in. But if you look at this picture here, what we are saying is, and what we are depicting, that if the value of x or your input, the number you are inputting into the function is less than equal to 5, then it returns you 0. And if the value is greater than 5, it returns the value 1. So it's kind of unit functions, and it's been used at some places where you need to set up some kind of threshold that if the value is greater than this, return me this value. If the value is less than that, return me that particular value. But it has not been used extensively throughout the program. Now comes the hero of activation functions, and that's called sigmoid or logistic activation function. What it does it, when you give some number to this function, it maps the output value between 0 and 1. So if you give any value between minus infinity to plus infinity, it can convert it between 0 and 1. That how it is helpful in terms of predicting the probability for an event. So if the value we are inputting is positive and bigger, the output from this function would be closer to 1. If we are inputting a negative value, the output would be lesser value. For example, x is equal to 1, then output would be 7.73. If it's 10, it's very close to 1. You can also think of just putting some value into the function, and it maps it values between 0 and 1. Fourth function is called tan hyperbolic or tan-h, and what it does is that for a given input value, it transforms it into in between -1 and +1. So something like logistic function converts the values between 0 and 1. It's very similar in nature like sigmoid activation function. The only difference is instead of converting the values between 0 and 1, it converts the value between -1 and +1. And for the value of 0, the output is 0. However, for a value of input 0, the sigmoid returns 0.5, and you can easily understand why. If we input 0 here, then e to the power 0 would be 1, and 1 by 2 becomes 0.5. So this is the point when input is 0. As far as implementation is concerned, sigmoid is being used in the output layer, so we can predict whether the probability of event is. tan-h is being used, though we haven't discussed the architecture, but it is being used in a lot of mathematical computations in your neural network to derive the best values of weight. Another activation function is called ReLU, and this has actually transformed the entire learning process of neural network. That's called rectified linear unit. And though it looks very simple that all it's doing is for all the values of input are less than equal to 0, it returns 0. But for all the values positive, it returns the same value, so it becomes linear for all the positive values. Though it looks very simple, but let me tell you, it has changed the entire paradigm of neural networks. This is the algorithm, or this is the activation function being used for deriving the most intelligent weights in neural network. Softmax activation function is very similar to sigmoid from the point that it predicts probability, but it works very well when you have number of classes more than 2. So if you're working with more than 2 classes, it converts them in the probability term, and I can see there is a major typo. It should be 0.01, 0.01 and 0.01 because it should be summing up to total value of 1. So what it does is that it gives the probability for each class of an event, and then it should be summing up to 1. So let's say there are 4 categories, category A, B, C, D like here. So it'll be giving what is the probability of an event happening in class A, let's say 0.5. Here it's 0.3, 0.1 and 0.1, and it would be summing up to 1. So softmax is also being used in binary cases, but its major implementation is when you have classes more than 2. The output is very similar like sigmoid does, but it's for more than 2 classes. So this is a brief introduction on activation functions. So we are importing NumPy library as NP. You can define your own functions. This particular way, you can define your own custom functions if you need to do your own calculations. So DEF, def or define is the word for telling the Python that you are writing your own function. And if I just talk about the syntax, what we are doing is we are giving the name of our function, then we are saying that we need to provide an input, and once we do the input, what it should return. So return is like what the value it will be giving back when you have run. It should be giving 1 divided by 1 plus np.exponential. It means we are calling the exponential from NumPy library, and then minus a. So whatever value you give here, you put into this particular formula, return the value. I'm doing it for these many values of a, and I'm running for most of the values. Let me just do it. What it's doing, at first it's running the sigmoid activation function for 1. So if the value of a is 1, this is the output, your sigmoid activation function there. If the value of a is 2, it becomes even bigger. So as I was saying, that value, when your input, the number you are giving to a sigmoid activation function is positive and bigger, it will be closer to 1. So if you see, I have given value of 4, it's very close to 1.98. When you give 5, it's in fact even further close. However, if you give a negative input to this function, the output is very close to 0. In this particular way, your model is being able to do predictions between 0 and 1. And if I give the value of 0, it returns the value of 0.5. However, these activation functions are also available in TensorFlow. where you can just call them rather than you define this function. So here I have written 10H activation function, here ReLU. So ReLU is very simple. So all you have to do is you have to return the maximum between 0 and the number. So if this A is greater than 0, it will return A. And if it's A is less than 0, it will return 0. So you see how easy ReLU's implementation is, that once you run it, all I'm doing is I have written the ReLU function, and all I'm doing is return me the value. If I input A is equal to -4, what would be the ReLU of A? So if I do it for -4, it returns 0. For -2, it returns 0. For +2, it returns +2. For +4, it returns +4. So in this particular fashion, you can write all your functions, and same I have done for softmax and sigmoid. So rather than defining these functions, you can call TensorFlow sigmoid, TensorFlow 10H, TensorFlow nn.relu. So nn stands for neural network in TensorFlow. But for ReLU, you need to call it this way, and it will give you the output as expected from the above formula. In TensorFlow or in this deep learning architecture, it is always a good idea to initialize your weights with some random numbers. And there is a function in TensorFlow called truncated normal. The truncated normal is that it will be generating value, normally distributed numbers with mean 0 and 1 standard deviation. However, this truncated word comes from that all the values which will be generated from this normal distribution would be only from ±2 standard deviation and not beyond it. Truncated normal is being used so that you don't have extreme values from the distribution, and all the values you are generating from this particular distribution are between ±2 standard deviation with 0 mean. How does this architecture or mathematical architecture got the name of neural network in first place? So the intuition for this kind of architecture of a learning algorithm comes from biological neurons, and people who come from biology background would already be familiar with this kind of picture. But for others who are not very much familiar either with deep learning or with biological neurons, that's how it looked like. And there are three major components which have been used in building the deep learning architectures. And these three architectures, or these three things are, first one is called dendrites. And dendrites are nothing but these are signal receptors. So for an example, there are billions of biological neurons in human brain, and a lot of these biological neurons are attached to our sensory systems. For example, there would be a lot of neurons attached to our eyes, and when we see something, we receive signals in terms of light or something. And these dendrites, what they do is they receive this signal which is coming from the eye, because they are connected to the retina or whichever part of the eye which is processing the information. And once these dendrites have got the information, they sum it up in the nucleus of this neuron, and that's called cell body. So if you take the intuition, what's happening is from these different dendrites, information signal is being received, and then this neuron is summing up what is the total information coming in. And then the final point, or the third point from a biological neuron is called an axon. And what it does, it passes the total information which has been received through this axon to a next neuron which is connected to it, because one neuron would be connected to a multiple neurons, and there would be lot of neurons when put together. And when the information received from all these signals, which is coming from their respective cell bodies, reaches a particular threshold, your brain takes some decisions, and this information is being processed in the form of electric signals or electric current. This is the same architecture which in 1950s McCallum and Pitts came up with first architecture called perceptron, which kind of mimics this architecture of receiving signals, summing it up and passing it to the next level. And from there only we built the complex architectures in deep learning. And if you look at this architecture, this is very similar to a biological neuron from the perspective that we have some inputs, x1, x2, x3 and xn, w1, w2, w3 and wn. These are the respective weights. And what's really happening is from these arrows we are trying to signal that we multiply respective input. So x1 multiplied by w1, x2 multiplied by w2, x3, w3, and here in the cell body we are summing up the information. So this is like in the previous picture we are calling the cell body. Here we are calculating the total information coming from our inputs with the respective weights. And activation functions, nothing but mapping functions. And what these are doing here, that if this information which has been coming from the inputs with the respective weights, if it is beyond a particular threshold, let's say you are applying a threshold activation function, then your model would be outputting 1 or 0. So for example, let's say if the output is positive and it's 10 coming from these information, and you have put in a threshold activation function here, something like this: if this output is greater than equal to 10, then pass 1, else 0. Let's say this is the function you have applied, and given this information, all your activation function would be doing is it would be looking at this output, how much this outputted, and accordingly it will be passing the value. Given this kind of threshold function which I have written here, it is greater than equal to 10, yes, so the output would be 1. This is the process how a perceptron produces an output. So here we are just showcasing that this summation is nothing but the input with the respective weight. So here it's showing Wi and multiplication of xi, summation of this. And for bias term, how is actually being done is, before I go further, that for bias term what we do is we introduce a column or a feature in our model. Let's say x0, and all the values in x0, you say that they are all ones. And then we also introduce a weight called W0, which is nothing but what used to be a bias term. And in fact, how do we do actual implementation? Here it's showing Wi, xi, I starting from 1. So if you just change this I equal to 0, then you can easily do multiplication, because x0 is already 1 and you're just multiplying the bias term. In the actual implementation, you will see that we will be doing from I equal to 0. So we are adding a bias term, and for all the inputs in the model, we are multiplying with the respective weights. So that's how we can make it simpler from the implementation point of view. So we will be calling W0 as a bias term. So here that we have just introduced another column for x0, which have all the values of 1. If I have a column x0 or feature which have all the values at every cell for all the training examples has 1, and then if I am multiplied W0, which is a bias term, you can easily understand I'm just getting the bias term for it. So given this understanding that how does a perceptron learn, so now let's come to an example of a perceptron. So for an example, if you look at this class and if you want to discuss this intuitively, what we do is that this is the actual data where we have 3 pictures of dogs and we have 3 pictures of horses. And what we want is, we want to create a linear classifier which can separate these 2 classes. So how would your model would be doing is, as I was saying, that initially these values of W0 to Wn would be initialized randomly. And this line would be created based on these random. And then you see what is the prediction and how many images have been predicted accurately and how many have been predicted inaccurately. And that inaccuracy is called error term. Let's say you have fit in this first line from the random weights, and you see this horse has been predicted as a dog and this dog has been predicted as a horse. It means there are 2 misclassifications, or number of errors are 2. Then in this next iteration, your model would be learning that in which direction your coefficient or weight should be changed so that this error goes down, and next line is being fit is this. So you have changed the coefficient values and this line get transformed into this line. And then you see again that how many errors are happening, and this time only 1 error because this dog has been classified as a horse, and number of errors is 1. And then the same iterative, the next iteration, you improve the weights so that the error goes down, and then your error is being reduced to 0. And this is the line which your model should be fitting. And we have seen that through the logistic regression, we also fit a line in the first module. In the learning process, we didn't go through how does the logistic regression learn that line. We just called a function from scikit-learn, and this function fit this line for us. But here we will be learning that how does your algorithm learn that this is an optimal weight, and we'll be going through the different building blocks of codes which help your model understand that this is the best line for the model, which is giving me the least number of errors. Let's take a very simple example. all of us should be familiar with AND and OR gates, and these are, you can think of it, it's a kind of classification problem, these two gates. So if I look at the OR gate, you will see that if any one of the gates are open, the output is 1, and if both are closed, then the output is 0. And you can also read it this way, that if x1 and x2 both are equal to 0, the output is 0, and if any one of either x1 or x2 is equal to 1, the output is 1. So you can think of it kind of a classification problem. And same is AND gate, where the output would be 1 only if x1 equal to 1 and x2 equal to 1, and in rest 3 scenarios the output is 0. And let's see how we can use a simple perceptron to solve this problem. So here, if you see, we have input and output, and all we need to do is that how does your perceptron would be helping. But if you want to see the process of how does an algorithm understand what should be the line of separation between two classes, so we can think that there are two classes, one is y equal to 0 and y equal to 1, and we can present it this way. So this particular point, if you see here, x1 equal to 0 and x2 equal to 0, and output is 0. We have showcased it with like non-filled circle, and for all other three, either x1 is 0 or x2 is 0 in these 2 points, and this particular point which I'm hovering over now, here x1 equal to 1 and x2 is also equal to 1. And now my objective is that I should be able to find a line which can separate these two classes. And let's see how does your model can fit this line for the model. So we know what the inputs are, we know x1 and x2 values, and let's say a model already have learned that weight associated with x1 is w1, which is equal to 1, and w2, which is weight associated with x2, is also equal to 1. And here we are considering that, let's say your bias term, which was b, is equal to 0, just for example purpose. So if you look at the first example, if I want to do output for this section, how do we get the output? That we get the summation of all the inputs with the respective inputs. So if you see x1 multiplied by w1, so x1 value is 0 and w1 value is 1, so this section becomes 0 plus, again for second term, which is x2 multiplied by w2, because this is 0, this term again becomes 0, and the total output for the first example is 0. Now we have put in a threshold activation function where we have fit in such a way, if the output coming from this is greater than 0.5, then give me the output 1, else 0. And because the output for the first example, which is here, is coming 0, and 0 is less than 0.5, which is the threshold, your model would be giving the output of 0. The same process if I do for the second example, x1 multiplied by w1 would be 0 because x1 is 0, plus for the second, x2 multiplied by w2, because this is 1 and this is 1, the output is 1. And then I again pass through this 1 with the activation function, which is 0.5, and 1 is greater than 0.5, then your model would be outputting 1. So that's how for each one of the examples your model would be multiplying the inputs with the respective weights, and with the help of threshold activation function you would be measuring what output should be given, and your model would be able to classify in which cases your model should be outputting 1 and in which cases it should be outputting 0. Let's look what does the process really look like. And when I was saying trying to draw a different line, if this is the case where there are some blue dots and there are some green dots, there can be infinite number of lines which can pass through. We are showcasing 3, but any number of line can pass through, and your model's objective should be that it should choose the line which is the best fit. It means which is giving me the least errors in terms of prediction. So how does it learn? There are a few steps involved. So we have some inputs, and I'm talking about a scenario where we need to produce some kind of classes. Let's say you need to predict whether something will happen or not. So you have some inputs in terms of your features x1, x2, xn features, and you have your dependent variable or class variable y. So how do you do that? First you will initialize these weights and the threshold or any activation function. You can say that I'm putting all my weights equal to 0. Or you can say that I'm randomly generating numbers for my weights between 0 mean and 1 standard deviation. Then given this randomized weights, you have inputs in terms of x's and also the output feature. and then you make predictions after multiplication of respective weights with respective features and applying the activation function, and then compare how good your model is doing. So how good your model is doing, you compare if the actual value was 1, your model was predicting 1 or not. So this is the misclassification error you calculate, and then this equation may look very confusing or intimidating in the beginning, but it is not very difficult. We have calculated the error, and error would be difference between actual minus predicted values. So this error we will be calculating, and then we'll be updating our weights in a way so this error get minimized. And this equation is used in terms of updating your weights in the direction so that your error term is reduced at each iteration. This equation would be used in updating all of them in the direction so that this error term is minimized. What really happens is that weight at the next iteration, and J is like, either W1, W2, W3, J is just representing that weight. Weight at the next iteration would be weight which was earlier plus eta. Actually, eta is called a learning rate, and then this is the error term, which is the desired minus actual, and then multiplied by the input. But basically your weights would be updating in the direction so that the total error from the model is minimized. And this process between 2 and 3 would be repeated till the time either the error has stagnated, or also you can repeat this process for a fixed number of iterations. So you can say that, okay, repeat this learning process 400 iterations. This is an overall process, and actually this does not change for any one of the learning algorithms. Either you're talking about machine learning algorithm, or you're talking about a deep learning algorithm, or you're talking about unsupervised. Actually the process remain exactly the same, in which you initialize some weight, you have your inputs, you measure how good your model is doing and how good it in terms of errors, and with the help of error you keep on improving these weights so that the error is minimized. And this process, as I said, is common across all your machine learning and deep learning algorithms. So this is, as I was saying, it is the process which all algorithms follow in terms of learning. Let me give you an introduction to two new terms. First thing is called a learning rate. What is a learning rate? Learning rate is an amount of size your weight should be changing. And let me give you an intuitive understanding. What does it really mean? Any weight W in the next iteration would be changed in such a way that from this equation, eta, this is some value you will be finding from some process. Let's say this is some constant term 10. If I change the value of this eta, the speed at which my W1 would be changing at iteration would be different. And what I mean, if I keep eta at 0.1, then in the next iteration, my weight would be adjusted with 0.1 multiplied by 10, it means equal to 1. So in the next iteration, my weight would be whatever weight it was, and I'm adding this term which is equal to 1. However, if I put eta, which is again a value which you would be providing a model, if I fix that eta is equal to 0.01, then what is the total output from, because this is, you can think of it as a constant 10, then multiplication is 0.1. In this particular way, in the next iteration, your W1 has been changed only by 0.1. So your eta is the step size, or the step your weight would be taking in terms of changing. If you keep this eta high, then your weight would be changing more frequently and more aggressively. If you keep this low, your weight would be taking smaller steps in updating them. Though both of them are going in the right direction. Let's say we need to update it, but this particular way, when we keep the eta at 0.1, your weight is changing 1 at every step. However, if I keep it very simple, your weights are updating with a smaller steps. And eta is being used in terms of controlling how fast and slow your model would be learning. Another thing is epochs. So till now, we have been discussing these words called iteration. So when you say iteration, that I'm running it 1,000 times, so basically I'm saying that I'm running 1,000 iterations of it. So the weight adjustment will be happening through learning from all the training examples. Let's say you have 100 training examples in your data, and the errors you will be calculating from your initialized weights on all these 100 examples. So like we have seen in logistic regression, we saw what is the accuracy percentage, and accuracy percentage is again one of the ways of seeing how good your model is doing. So this learning process is taking all these 100 examples, going through all of them to change your weights in the right direction. So epochs means that how many times you go through all these 100 weights in the learning process. So you will be deciding that you need to run your optimization algorithm for how many iterations. So let's say you say, I want to run it for 1000 times. So your model would be going through training examples 1000 times and changing the weights. And after 1000 iterations, you will be saying what is the final weights. And this iteration is called an epoch. So this is the IPython notebook, and let me zoom it a bit if I can. So first thing which we need to learn here is called the loss function. But the loss function is basically, if I take an intuition path, it is an indication that how good your model is doing. If there is loss of loss, it means the model is not doing good. If it's accurate or 100% accurate, there is no difference between actual value and the predicted value. So this is the definition which comes from TensorFlow website. It's like a loss function measures how far apart the current model is from the provided data. There are few metrics which are being used in measuring how much the loss is, and it'll depend the kind of problem you are going to solve. For example, if you're working with regression problem where you are outputting some kind of numerical values, MSC, mean squared error, is something loss function which is extensively being used, though you can also use MSC in terms of classification problems where you take 1 or 0 as your output value, and the probabilities, let's say you are using sigmoid, which would be between 0 and 1, and you take the difference between actual value and the predicted value. Though it is possible and you can use it, but there is another loss function being called cross entropy. Entropy is a loss of information if you talk about in signal terms, and cross entropy is an loss function which has been extensively being used for most of the classification problems. So let's take a toy example. Here we are trying to see that what is the loss. If you see that we are importing the TensorFlow STF, we are initializing two variables and we are just fixing the value for now, 0.3 and minus 0.3 for W and our bias term. We are initializing X and Y, and what we are doing is we are writing an equation which is like your output is weight multiplied by input feature plus the bias term, and squared delta, which I'm calculating here. Actually, this is the difference between the actual value, which is Y, and the predicted value, which is the linear model. And TF dot square is helping me taking the square of each difference. Why we are doing square? It's the two reasons we take square. One, we'll be seeing at the time of optimization that we take some derivatives. So taking derivative of a square term is pretty much simple in comparison to absolute value. And second, there may be a difference between actual value and predicted value, which may be, some case it will be negative, some example will be positive. And if I sum it up for all the examples, this difference, it may come to 0. You may have this understanding that your model is doing a great job, which is not. And the loss is you are taking squared sum. So here we have taken for all individual values, and reduced sum actually in TensorFlow is taking summation for all the examples we are taking, and then all the values coming from here, we're taking the square. This line, if you recall, was for initializing all the variable data type in the model. So global variables initializer help me initializing the values of W and B, and then you run a session. And then you need to provide these values with the help of feed dictionary. And I'm saying X is equal to 1, 2, 3, 4, and Y is equal to 0, minus 1, 2, minus 3. And then you run. So what your model is doing, it is producing the output with the help of input, which is X, and the weights and bias term which I have initiated on top, 0.3 and minus 0.3. It's multiplying the weight with all these values, then adding the bias term, and then we are taking difference for all the 4 examples we had, and this is the total loss we are getting from this model. So loss function is kind of indication that how good and bad your model is doing. Now comes the process of optimization, and this is the core of learning. one way to calculate the difference between actual and predicted. If the variable you're trying to predict is a numerical variable, like in the case of regression, you can take help of the squared difference algorithm, and it will be useful in predicting how good a model is doing. So it's the squared difference. But in case when we have categorical values, we use a different function or a different loss function, and most of the time we use cross entropy. And let's take the cross entropy first. So I have created a very simple and with a very small example just to give you an intuition that how does your model learn how much the cost is using cross entropy. So I'm taking an example. Let's say you have two features, x1 and x2, though it's the same values, but let's say I'm just calling it x and x1. And there are three classes in your output variable, class 1 to 3, and there are 7 customer data you have. So because I know there are 3 distinct classes in my dependent variable, I can represent it with one-hot encoding, something like this, that I can represent class 1 as 100, class 2 as 010, class 3 001, and this thing would be repeating, so class 1 again 100, and so on and so forth for all the examples we have. Now, just this section, you think that we have got some output. So if we have 2 features or 2 variables, x and x1, then there would be 2 weights associated with them, and we will be producing some kind of output. So let's say here the weight was w, and here the weight was w1. So these are 2 weights respective to each variable, and whatever the multiplication is coming, w multiplied by x, w1 multiplied by x1, this is the output you are getting. Then if I have got these outputs, and given these are representation in one-hot encoding, at the time when I was explaining the activation functions, I mentioned that softmax is an activation function. What it does, it converts the output coming for each class into a very nice probabilistic term. In the same way, we have sigmoid activation functions. So for an example, if I just take this example, which is highlighted here, that for customer 1, for 3 classes, this is the total score came in. And what is the function for softmax was that you exponential of the value and divide by summation of all the exponential values. So what I have done is I have created exponential of all these values, individual values, so exponential of 3, exponential of 5, exponential of 2, and then I converted in terms of the probability term. So this 20 divided by the sum of all 3 values. And now if you see, the summation should be 1 for all the 3 classes. And basically what your softmax tells you, that wherever the highest probability is, your model is predicting that particular class. And in this example which I'm highlighting here, actual value was this, it belonged to class 1. However, if you see, our model is predicting highest probability for class 2. So probability for the second class is highest, and the model output would be actually class 2. But our actual purpose of discussing this particular example was the loss function. And the function for this is very simple. It is summation of y multiplied by log of p. And if you see this function closely, when I say y multiplied by log of p, and p is the probability for that particular class, then we need to do multiplication only for the instance where y equal to 1. Rest of the things it become automatically 0 because y becomes 0. Let me take a step again. We were presenting the first example as class 1, and these 3 is 100. If you look here, all we are doing is value for only first class, it is coming 0.94, and rest of them it is 0. Given for these class 2 and class 3, this is already been represented by 0. So cross entropy is also a very efficient mathematical operation for identifying the cost, only measuring where y is equal to 1. And in intuition terms, what we are doing is that your model 1 was expecting 1, you predicted 0.11, what is the total cost? And the function is if the output for the particular class is closer to 1, and you know that log of 1 is what? 0. Then the loss for that particular example would be 0. However, here we expected 1, which is the actual value. Your model is giving 0.11, so this is the loss. So if you see the function in end is nothing but with a negative in the beginning, E3 multiplied by log of Q3, and Q3 is the probability coming from the softmax function. And we will be calculating, if you see that we are getting, for second example, it was class 2, and for class 2 the probability is 0.24, and this is the loss we are getting. Let me see for one of those where the loss is very close to 0. So if you look at this, we were expecting it was the class 2 example. However, the probability is very, very close to 1 and almost 1, given that all other values are very negligible, and loss becomes 0. So what cross entropy does is, if your model is predicting close to 1 for a particular example, then it's very less. But if you predict lesser probability, the loss goes higher. And end of the day, all you do is, for calculating loss of the entire training data set, you sum up all the values from these cross entropy terms. There are different and other ways of calculating cost and loss function. However, the MS for numerical outputs and cross entropy for classification outputs is most of the time being used as a loss function. So optimization process is that you update those weights which are associated with input values in a way that your loss is getting reduced and reduced. So you would have seen this kind of implementation and explanation from people like Andrew Ng and Geoffrey Hinton, and if you're reading some machine learning book, they also have taken the similar intuition. What we have done is we have created more tutorial only. But think of it, it's an example that somebody is on top of a hill and he wants to come down on the ground level, and he's blindfolded, and only thing he has a stick like blind people have. But he wants to come down directly, and the only objective he has that he should be able to come down as quickly as possible. So how he can decide that which is the correct way or right way of going downwards? Let's say there are 4 ways he can go down. He can take this path, he can take this path, he can take this path. There are other ways which will be the other side of the mountain. So what this person can do is, from his stick he can just tap around and see whether he's going downwards or it's a flat in a particular direction. And if you see, intentionally we have kept that the direction of the slope is different. So if you see, this is a kind of more steeper in comparison to this slope which I'm hovering over. So if he taps around in 4 directions, he can see, okay, which is the more steeper one. And if he takes the steeper path, he would be able to reach the ground more quickly. The same intuition is being taken by your learning algorithm. And this person wants to reach the ground level as soon as possible. Your model's objective is also that you should be able to reduce the loss or cost term as quickly as possible. And how you can do is, if you improve the weight in the best possible direction, then you'll be able to reduce the loss more quickly. And if I take this intuition, let's say he taps around and he sees, okay, this is the direction which will take him very quickly downwards. Then another intuition, that how far he can go, whether he can take 2-meter step, or he can take 1-meter step, or just half a meter step, that would be controlled by, as we saw, in terms of a learning rate. So how big a step he'll be taking, that will be decided by the learning rate in our algorithm. So let's say he can take this bigger path in one instance, and he has seen, okay, this is the most steeper one, so in 1 step he reaches here. And then what he does, he taps around again and see which is the steeper direction, and then take 1 more jump or 1 more step going downwards. Then he taps around and then see which is this direction he needs to move in, and then he takes another way. When I say he taps around and see which direction he moves, it is being decided by the algorithm and which we'll be using, which is called gradient. Gradient is first order differentiation, which help you understand then in which direction your function should be moving to minimize the cost. At each step it keep on doing the stepping around, and then he reaches the bottom. The same intuition is being taken by your learning algorithm, which is called a gradient descent. And when you say reaches the ground in our algorithmic terms, we can say that we have stopped reducing the loss function. Our loss function has been reduced to its minimum, and it's not reducing any further. This minimum value, where your loss function got minimum value, is called global minima. So in TensorFlow, for doing this stuff is called gradient descent optimizer, and there are a few variants of it. It is the most basic optimization algorithm for helping your model understand that which direction your weight should be updating. We have initially started W with 0.5 and B at 0.1. So this is the initial value. You can think of that you have randomly assigned value of 0.5 to W and 0.1 to B. And we have created two placeholders for our input and output feature. And we have created a function for calculating the output. For a given example, this loss function is the same like we have used in the last explanation. We are taking the difference between actual value and the predicted value and taking square of it. And then we are calculating the total loss by taking sum of. And now in TensorFlow, to reduce loss and updating these weights in the direction so that these weights are minimized, I'll be calling an optimization function called gradient descent, and I can easily call it by tf.train.gradient descent optimizer. So this is the way you call the gradient descent optimizer. This particular value, if you see here, this is the learning rate value, that how big the step your model would be taking in terms of updating. So whatever value initially starting here, how much it would be changing. So step size would be decided by this. Then you need to train your algorithm, and what you need to do, you need to call this optimization function, though it can be done in one line, but I have put it in 2 lines. You could have put it minimize this loss here itself. But what we are doing is we are creating an optimization model or a function we are calling. And then what our intention is that we should be able to minimize the loss function, which is coming from here, which is sum of squared distance between actual value and predicted. And how we do it by calling this optimization function, which is a gradient descent. Then we are calling this function for initializing the variables. So we initializing 0.5 and 0.1, starting a session, and we are giving the value of input and output. And then I'm printing the value of W and B. And this is the most important thing which you need to think of, these 2 lines. For I equal to 1 in the range of 3. So what we'll be doing, we'll be running this model 3 times. 0, but this kind of line, what it does is, if I do it, it will be actually, all we are doing, we're running it for 3 times. But if I do it, print, so all I'm doing is it's producing 3. So all we are doing is for every times we want it, just run the train function on these training examples which we have. And when it's done, because it's out of the loop, what will be outputting is whatever the learned weight of W and B are. And if you see that initially the value of W were 0.5 and B were 0.1, and then it has been changed to, W's weight is changed to minus 0.54 and B's value has been changed to minus 0.24. And if we run it for more number of iterations, it will be changing further. So if you see the loss when you had weight at 0.1, this was the loss. When you have 0.2, this was the loss. When you had this, you keep on seeing that. And at W equal to 1, your loss was 0. But if you increase it again to 0.1 and keep on increasing, your loss is again keep on increasing, because now your predictions are again going in the opposite direction. How your model see it, actually something like this. So initially that was your total loss. What your model does, this gradient descent, it takes a derivative at this particular instance and see which direction it should move. And it says, okay, this is the direction you should move. So you need to increase the weight. And increase the weight by how much? One would be the gradient value which would be coming from derivative, but also what you are multiplying the learning rate. So let's say you have fixed the learning rate at 0.2 or whatever number you have fixed. So this is the step size you keep on taking. So from here you have reached this particular value. And then at this particular point you again take the gradient and see which direction your weight should be moving. Your learning rate help you how much the step size would be. And then it changes here, and each step you keep on calculating the loss or the cost of it. When it reaches there, your gradient become horizontal and your model will not be changing the weight, and you can say your model has converged. Why I have shown you both the ways, that it is a perfect possibility that rather than initialing your weights at 0.1, you could have started with weight equal to 2, and then your model does the same process. It measures the gradient, see which direction it needs to move, and then keep on going in the direction where the loss is going down. Basically, in the text, you won't see both the directions. Most of the time, you get to see half of the picture. This would be kind of your loss function when you'll be actually implementing a model, that you start from a place and your gradient descent algorithm would be helping which direction it's to move. And with the help of learning rate, you'll be deciding how would be the step size, and you keep on going in the direction. And once your model has reached, or model has kind of identify the weights where the loss has become almost negligible or very, very less, you have this line going something like this. But this process is applicable because, as I was saying, you are supposed to randomly initialize weights, and it's a perfect possibility that rather than starting the weights from point 1, you could have started from as a weight of 2 or 3, whatever weights are there. Then even in any one of those situations, the learning process remains absolutely same. So that was the reason I wanted to show you both the size, but this is what happens in the back end. So initially we started with weights of 0.5 and 0.1, and we created a loss function as sum of squared differences. Then we called a gradient descent, and what gradient descent is actually doing is it's changing the weights from these values which we have initially given to our model. These are being changed in the direction so that the loss is going down further and further. So this is the way your model learns. And loss function and optimization function, these are two most important building blocks, and this is one of the very important stuff in machine learning and deep learning. So minimum value in any function, if I look that this is the function I have, if you look, I can start my values from anywhere and I can go to value anywhere. This would be my type of function, and people who come from mathematics background would know that this is a convex function because it's a squared difference between values. We always get this kind of function. You can change the w in any direction. You will end up getting this kind of graph only. There is no other way that you will be getting any other kind of graph. And people who know it, it's quadratic equations graph. Given that this kind of function has only one minimum value, you start from any direction, you can start from plus infinity to minus infinity anywhere and keep on changing the weights. There would be only one minimum value in this kind of function. So convex functions always have just one minimum value, and given it has only one minimum value, that's called global minimum, because this is the minimum value of your function itself. And if your loss function or cost function, if of quadratic function nature, there can only be of one value, and once you reach this value, you can run your model for thousands of iterations. This weights will not be changing because the gradients has become parallel and there would be no change in your weight. But actually this is not always true, because you will be dealing with different kind of cost functions. I have used the squared one here, but let's say you are using the absolute difference one as your cost function, then there is a possibility that you end up getting this kind of slope or this kind of graph for your cost function. And when we say local minima, this particular point which I'm hovering over now, it is, let's say you have reached this particular place while learning the example, and if you take the derivative here or the gradient here, it'll again be parallel to the axis. So your model may be thinking that you have reached already the minimum value possible for your cost, and it stop updating your function or your weights. And all these values here are called local minima. And if in this particular function, this is actually the global minima, because this is the most minimum value possible for this particular equation. So if you're using kind of square activation cost function, then you don't have to worry about the local minimum, but you should be aware about these things, that there may be a possibility if you're using different kind of loss functions, you may have local minima in your cost function, and there are different ways of dealing with it. Like you initialize a weight most randomly as possible, so there is less probability of getting at a specific place, or there are other methods that you can change the type of loss function you're using. So now what we'll be doing is I'll show you an implementation in TensorFlow for one of the use cases which we have already implemented in the case of logistic regression using the same data set which we had earlier. So we are importing these libraries, and these are the same basic libraries. Only one library which is new is this TensorFlow library. The rest of the stuff is same. Then we are reading the data, the Sonar CSV data which we had. So we had values of y as something like this, and now we have created one hot encoding. For 0 we are presenting it 1 0, and for 1 it is 0 1, and for 0 1. So given this, next we are coming to the normalization process. It was important in machine learning to normalize the features to either with a 0 mean and 1 standard deviation, or between 0 and 1 with max min, or any other normalization. But you need to bring all your input features to one scale. And this is one of the most important steps which needs to be taken before you implement any one of the deep learning algorithms. If your features are not normalized, your model will learn. One, it may take a lot of time, and also it will be taking a lot of time to converge. When I say converge, like to identify the most optimal weights. Here we are doing normalization, the normalization process. It's like taking the value, subtracting the mean of it, and dividing it by the standard deviation of the data. And what it does, it will be normalizing the features. And we have done it for all the features in one go. We will be calling this function to do this task. Appending the bias term. So what we do is we introduce a column. As I was saying, that we introduce a column with all the values as 1. So it will be something like we have introduced a column of the same length as other features are, and here the values would be all the places 1. And as I was explaining, the purpose of doing this is so that we can do this implementation pretty quickly, because now we can do W0 with X0, and W0, as I was saying earlier, we will be introducing as a bias term, which we had as B. And now, because we'll be doing the matrix multiplication, we can easily do this summation from I equal to 0 to n. N is the number of features you have, and you can do as Wi xi. And this is for plotting the values we have in the data set, so that we can see how our two classes 1 and 0 is being intermingled with each other, whether these are linearly separable. And that's one process you can use it to see whether you should be able to use a logistic regression for a given problem, or you need a more complex algorithm. And if you see that all these values between the red dot and the crosses, they are kind of intermingled, and there is no one line which can separate those. So either we need a complex algorithm, or people who are very much inclined towards using machine learning algorithms, you need to do kind of data feature extraction so that those features become linearly separable. But here we are using neural network, which would be helping us separating these two classes. That's how your X values look like. So these are all the features we have. And if you see that these are the values of our Y variable, these are all ones. And that's the reason why we need to shuffle our data set. And we do it because that there may be a case of something like this, where all the values are on top are of Y equal to 1 examples, and all the bottom examples are of Y equal to 0. So shuffling this was kind of distribution equally, that we don't have this kind of distribution. And then we are dividing our data into two groups, as we have already seen in the regression and logistic regression, that we are splitting the data into two groups, train and test. So 80% for training and 20% for test side. Random state is like so that you receive the same examples at the same time. And these are the shape that 165 is the number of rows and 59 number of columns you have. And in the training end, this is your training Y. So now if you see, it's 2 because every Y value is being dummy coded. So 0, as I was saying, 1 0, and 1 as 0 0 1. So first we initialize some of the hyperparameters, and as I said, we are just introduced two. We'll be, when we go through, we'll be learning more of hyperparameters, and we have introduced two only for a reason, that only these two hyperparameters are required. So first thing, learning rate. Learning rate, as we have understood now, it is the step size or the amount of change in each iteration your weight would be dependent on. It was something like that weight at t plus 1 iteration would be equal to weight at iteration t minus alpha or eta, and which was like both the learning rate, and multiplied by whatever the gradient is coming. So that's how your weights get updated, but your alpha or learning rate plays a role that how quickly your weights would be changing. We should always be putting the maximum value possible for learning rate so that your weights being learned as quickly as possible. And it's not a bad assumption or bad thinking, but there is a reason that we always be striving for the optimal value of our learning rate. And now let me take an example to show you. So let's say here we have taken some specified value of learning rate. But it is possible that suppose you started from here and you have taken a very big learning rate. So you have increased the learning rate to a very large number. And you started from here, and in one iteration, rather than reaching here, you have reached, let's say, here. And in one iteration, you have changed the weight from 0.1 to 0.7, and our loss has also drastically reduced. Earlier it was around 300, and now you have reached, which is almost close to zero. But it is not the optimal value, right? There would be some gradient here as well. And if your value of your learning rate is very high, in the next one or the next step, you will be reaching here because your learning rate is high. And then you have reached here, you take the gradient, okay, now you need to reduce, and probably next time you reach here. And this process, which is like keep on hovering over, you may reach the minimum point, then it will stop. But there is again a possibility that you kind of oscillating between the minimum value or the optimal value and the non-optimal values. And you may not be moving in the direction where your weights get optimized finally. This kind of problem is called model divergence in the text. And some of you may be thinking that it's not a very common problem. I can tell you with experience that this is one of the most common problems in making your own models work. And there are different ways of deciding what should be the learning rate. As a rule of thumb, you would have seen that people would be using somewhere between 0.1 to 0.01. And its variants that some people would be using 0.05 and sometime it's like 0.6 or something. So this is the actual range people use for learning rate, and it's not a bad selection actually, 0.1 to 0.001. So we have already seen that if we have a very big learning rate, we end up getting into this kind of scenario that we never reach the minimum value of our loss function and we keep on oscillating. And we can see it whether your learning rate is good or bad, because we will be storing, in the example I'll also show you, that why we store the loss of your model at each iteration or each epochs to be precise, so that you can see that your model is really learning or it's kind of oscillating in between. Your loss functions trend would be helpful in seeing whether it's doing good job or not. Okay, now I know that bigger learning rate may create this kind of problem. Why not choose a very small value? Let's say select this as a learning rate. And in this way, I know that I'll be taking smaller path, I'll be taking more time, but actually eventually I'll reach the minimum value. But I also said in most of the real implementations, you will be setting up that how many times you need to run your model. And let's say you have set 1,000. Why we do it? Because when you start doing your calculations or implementations on GPU, you have to be really conscious about how much time your model is taking to learn. And if it takes too much of time, you end up spending a lot of money, which is not worth. And if you have chosen a very small learning rate, your model would be taking very, very tiny steps in kind of, though it's going towards the minimum value of your function, but it's taking very, very simple short steps, and you end up taking a lot of time in reaching there. And let's say these are 1,000 steps and your model has reached only here, and you end up using these weights. So these are two reasons that you have to identify the optimal learning rate. And that's one of the most important hyperparameters for learning the model. Then this is training epochs, and this is the number of times or number of iterations you need to run your algorithm for. So we are saying run it 4,000 times. And here I'm setting up an empty array, and this would be helpful, as I said, that we'll be measuring cost at each iteration to see whether your model is doing good stuff in learning. And how do we know it's doing good stuff? That your cost would be reducing at each iteration or epoch to see that your model is learning the weights in the correct direction. Number of epochs, I also want to mention one more thing. Similar to learning rate, if you set up too many, let's say you set up this big a number of learning epochs, then your model will be taking too much of time. And if you take too less, like just say 5 or 10, then you will not be able to reach the optimal value, because that you have reached only, let's say, this position, and this is not the optimal for your model. So you need to identify, actually you need to play around with these numbers so that you take optimal steps so that you reach your minimum value with minimum number of epochs or iterations. And it can be very helpful from the point of view that your cost functions graph would be helpful in kind of telling you how good you are doing in terms of both these values. As a rule of thumb, we should start with a reasonable good learning rate, which is 0.1. And you should start with like 100 or 200 training epochs, not more than that. And only after looking at the cost function and graph, I'll show you that how do you interpret it, whether you need a bigger learning rate or whether you need more epochs. You can take a lot of help from graph of the cost history. So now we are putting what are the dimensions of your input shape. So you're getting number of columns. If you see, 1 is for columns and 0 was for row. And number of classes are 2 because we have 2 classes now, 0 or 1 being presented into 2 categories, 0, 1 and 1, 0, because we have done one hot encoding. You need to specify the X value, and that's what I was saying. It is very important that you need to specify the dimensions. We are creating X as the placeholder like we have already done for smaller examples, which would be of float 32 types, which we have for decimal values. This none means that it can be of any number of rows. So in this particular data set, we are training a model. We have, let's say, 159 or 200 training examples, but tomorrow you have 300. So you don't have to change this dimension. If you fix it, then you have to specify that how many rows are there. But if you keep it none, then your algorithm understands that it is changeable number, and whatever number of rows I get, just accept it as it is. And number of dimensions, you're telling that how many input features you have into the model. Though we are deviating on top of, we have a specified column for our biases, but we are doing the simpler implementation as earlier. But the more important point to take away here is this. We are initializing W with all zeros, and let me tell you, it is not a good implementation, but here we are initializing all the initial weight at zeros, and that would be of what dimension? If I need to do matrix multiplication, these two matrices have to be some kind of specific dimensions. And if I need to do matrix multiplication, let's say this is n by m, what should be the dimension of this matrix? At least m, and then I may have any number here. If number of columns of the first matrix is equivalent to the number of rows of the second matrix, then only you can do matrix multiplication. So that's why you have to make sure that weights you are initiating should be of the correct dimensions. And that's why most of the people make mistakes. If you interchange the numbers, if you see that this is the number of column and this is the number of rows, so that's why. And if you make mistake here, you will be getting a lot of errors. Then I'm initiating this bias term with all zeros with number of classes. There are 2 number of classes, so 1 bias term for each class. We are just initializing all the variables in the code and defining the y variable, the output here. So we are calling the softmax function, and what we are doing is the predicted value is tf.metmul of x and w plus the bias term. And the softmax, what it is doing is, so this is the placeholder for your actual values, and your actual values we are doing the same placeholder tf32. None is again because if you see here for x variables we are saying that it can be any number, and you would agree that we need to have as many number of rows for input features as many dependent variable, because one would be corresponding to each other. And number of classes, there are 2 number of classes now. So we are doing 2 operations. First we are calculating the total output, which I was showcasing in Excel file, that what is the total output for each class, and then I'm generating probability using the tf.nn.softmax function. So now we are doing this calculation and we are implementing the cross entropy, though there is a function itself as cross entropy, but here we are trying to showcase that we are multiplying y with the log of the probability we are getting for each class, and you end up getting number only for the class where y equal to 1, and then we are taking this negative and reduce sum. Reduction indices, if you call 1 is by column, so we are summing it up for all the columns and then taking the mean of all the value. So this is the total cost, and then we are calling the train optimizer. We could have done in the their example in 1 line of code. So we are calling gradient descent optimizer with the learning rate we have already initiated as 0.1 if I'm not wrong. And then what I need to do is I need to minimize the cost function which I have defined here. Then I initialize a session and I initialize all the variables in the model. MSC history, this is we need to store what is the loss is at each iteration. We are starting with an empty list, and then it's the same function which you have doing. Number of training examples we have done 1000, so all we are doing is that run these codes. You could have used I or anything, but because we call it epochs, so we're saying for epochs in the range of 1000, so run it for 1000 times. What you need to run the training step, which was the last step in our case. And all you guys know by now that everything in TensorFlow is kind of a graph, and if you run the last calculation, all other calculations will be on top, would be run accordingly. And feed dictionary, we have already defined what our train X and train Y are, and we can calculate the cost for feeding into our dictionary so that we can see how does it look like, and we keep on appending this cost to our each iteration so that we can see how does it's doing. And here in the line of code, we are predicting once it's done, make the prediction for the testing ones. It should print me 3 values, the epoch name and the total cost. And this is actually more important to see that whether your cost going down or not. So let me go at top. I have run this code already for you. It may be of different scale. Sometimes you have different numbers. But if it is reducing at each iteration, then probably it's an indication for you that your model is doing the good job. Your weights are being learned in the right direction, and your loss is reducing. So we started with 0.68, and if I keep on running it for 1000 times, it's reducing almost. There may be fluctuations, not everyone would be reducing, but if you overall see that it has gone down, then it's an indication that your model is learning. And we have just created a plot of it. All the 1000 iteration values, we have created this plot. And what it tells you, one, your cost is going down in a pretty optimized way, but it's going down pretty neatly. And I can see that this learning rate which we have selected is doing a good job in terms of reducing. And at the 1000 iteration, it kind of still going down. So had it been something like this, if your graph looks like something like this, then it's an indication that your model doesn't require a lot of iterations because your loss function has kind of tapered and it's not learning any further. If your loss function looks like this on the case of number of epochs, then it's an indication that your cost is going down. Eval is again evaluation function in TensorFlow. And this is, again, we are plotting the same cost. And if you see that, in my opinion, it has not completely flattened, though it has reducing a lot, not much, but still I see there is a scope that we can work with more number of epochs. And one thing you can try at your hand when you'll be running these codes, that you increase the learning rate at your end and reduce the number of epochs and see the best shape of your graph looks something like this. Thank you.
So thank you for the great session, Amit. I hope all of you found it informative. If you have any further queries related to the session, please comment in the comment section below. Until then, that's all from our side today. Thank you and happy learning.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!